Welcome, fellow dreamer. Tonight, we journey through the story of meteorology, tracing humanity's patient quest to understand the winds, clouds, and storms that dance across our skies. This tale unfolds accompanied by gentle music and abstract imagery, revealing forgotten wonders and quiet marvels from the history of atmospheric science. As you listen, let these stories satisfy your curiosity while guiding you softly towards sleep. So take a deep breath, settle into your pillow, and allow your mind to rest. Let your eyes grow heavy as we explore how our ancestors first learned to read the ever-changing heavens above. Long before there were weather forecasts scrolling across smartphone screens, before satellites circled the Earth capturing cloud formations, before instruments could measure temperature and pressure, there were simply human eyes turned upward toward an ever-changing sky. Our earliest ancestors, living tens of thousands of years ago, possessed no scientific instruments, no mathematical equations, no written records. Yet they were meteorologists in the truest sense, observers of the atmosphere whose survival depended entirely on their ability to read the subtle messages written in clouds, winds, and the behavior of the world around them. Imagine those first humans emerging from their caves or simple shelters each morning, scanning the horizon with eyes that had learned to notice things we might easily miss today. The color of the dawn sky held meaning. The direction of the wind carried information. The shape and movement of clouds told stories about what the day might bring. These observations weren't merely interesting curiosities, but matters of life and death. A sudden storm could endanger a hunting party far from shelter. An unexpected freeze might destroy gathered food stores. A prolonged drought could force an entire group to abandon their territory in search of water. These ancient weather watchers developed their knowledge through pure observation, generation after generation, noting patterns and passing them along through oral tradition. They noticed that certain cloud formations preceded rain. They observed that winds often shifted before a storm arrived. They recognized that animal behavior changed when weather was about to turn severe. Birds flying low, insects becoming more active. Even the smell of the air itself became part of an intricate web of atmospheric awareness. As human societies transitioned from nomadic hunting and gathering to settled agriculture, understanding weather patterns became even more critical. The first farmers, appearing around 10,000 years ago in various parts of the world, needed to know when to plant their seeds and when to harvest their crops. They had to predict the arrival of seasonal rains and anticipate the first frosts of autumn. An entire community's survival rested on these decisions. In these agricultural settlements, certain individuals likely emerged as particularly skilled weather observers, people whose predictions proved more accurate than others. Perhaps they were elders who had lived through many cycles of seasons and developed an intuitive sense of atmospheric patterns. Perhaps they were shamans or spiritual leaders who combined weather observation with ritual and ceremony. Regardless of their role in society, these early meteorologists became keepers of accumulated weather wisdom, living libraries of atmospheric knowledge. The earliest farmers learned to associate weather patterns with the movements of celestial bodies. They noticed that the sun's path across the sky changed throughout the year, rising and setting at different points on the horizon as seasons progressed. They tracked the phases of the moon and observed how lunar cycles sometimes correlated with weather changes. They identified particular star patterns that appeared in the night sky, at times associated with specific seasonal weather. In coastal regions and along great rivers, understanding weather became intimately connected with water in all its forms. Communities living by the sea learned to read the ocean itself as a weather indicator. The size and character of waves, the behavior of tides, the temperature of the water, all provided clues about atmospheric conditions. Fishermen developed sophisticated knowledge of local wind patterns and could sense approaching storms through subtle changes in sea conditions that might escape a landlubber's notice. Navigation, whether by sea or across vast landmasses, demanded weather knowledge. Travelers needed to anticipate when conditions would be favorable for journeys and when it was wisest to remain sheltered. Polynesian navigators crossing thousands of miles of open ocean developed extraordinary abilities to read weather signs, interpreting the clouds, winds and swells to guide their vessels safely between distant islands. Their knowledge, passed down through apprenticeship and oral tradition, represented generations of accumulated atmospheric observation. Different environments produce different types of weather expertise. People living in tropical regions develop deep understanding of monsoon patterns and seasonal rainfall cycles. Those inhabiting temperate zones learn to recognize the subtle transitions between seasons and the weather patterns characteristic of each. Arctic peoples became expert readers of ice and snow conditions, understanding how atmospheric factors influence the frozen world around them. These prehistoric and early historic peoples created the first weather predictions through pattern recognition. They understood that weather wasn't entirely random, but followed certain rhythms and tendencies. While they couldn't explain the physical mechanisms behind atmospheric phenomena, they could recognize that similar conditions often produced similar results. When the sky took on a particular appearance, when winds blew from a certain direction, when temperature and humidity combined in familiar ways, experienced observers could make reasonable predictions about coming weather. The development of language allowed these observations to be encoded in memorable forms. Weather lore emerged as a way to transmit atmospheric knowledge across generations. These weren't scientific formulations, but practical wisdom distilled into forms that could be easily remembered and passed along. Some of these early weather sayings, born thousands of years ago, would persist through millennia, their origins lost to time, but their observational accuracy enduring. As human societies grew more complex and interconnected, weather knowledge became something that could be compared and combined. Traders traveling between regions might share observations about weather patterns in distant lands. Coastal communities might exchange information about storm behaviors and seasonal wind shifts. Gradually, individual groups' weather knowledge began to contribute to broader, more comprehensive understanding of atmospheric patterns across larger geographic areas. By the time writing systems emerged in various civilizations, humanity had already accumulated thousands of years of weather observation and prediction experience. The knowledge remained largely practical rather than theoretical, focused on what the weather would do rather than why it behaved as it did. Yet this foundation of careful observation, pattern recognition, and accumulated wisdom represented humanity's first steps toward understanding the atmosphere. These ancient skywatchers, whose names we will never know, were the first meteorologists. They established the fundamental principle that weather follows patterns that can be observed, recognized, and to some degree predicted. They developed the essential skill of patient observation, watching the sky not occasionally but constantly, building mental libraries of atmospheric behavior. Their legacy would flow forward through time, eventually giving rise to more systematic approaches to weather observation that would emerge in the early civilizations of Mesopotamia, where weather watching would take on new dimensions of organization and record keeping. The great rivers of Mesopotamia flowed through a land where the sky demanded attention. Between the Tigris and Euphrates, in what we now call Iraq, ancient civilizations arose that would transform weather watching from casual observation into systematic record keeping. Here, under vast open skies that could shift from brilliant clarity to sudden fury, the Babylonians and Assyrians developed something remarkable: a methodical approach to documenting the heavens and the atmospheric changes they witnessed. The scribes of Mesopotamia possessed a tool that would prove invaluable for preserving knowledge across millennia. Clay, abundant along the riverbanks, could be shaped into tablets while wet, inscribed with cuneiform wedge marks, then baked hard as stone. Upon these humble tablets, weather observations were etched with careful precision, creating archives that would survive thousands of years buried in the sands. When archaeologists eventually unearthed these ancient libraries, they discovered that the Babylonians had been watching the sky with extraordinary dedication. These early Mesopotamian observers understood that the heavens and the weather were intimately connected in ways that mattered deeply for their survival. In an agricultural society dependent on irrigation, unpredictable rainfall, flooding rivers and violent storms could mean the difference between abundance and famine. The priests and astronomers who maintained observatories atop ziggurats took their work seriously, scanning the horizons each day and night, noting every phenomenon worth recording. The tablets reveal a sophisticated system of weather observation that began around 2,000 years before the Common Era and continued for centuries. The observers tracked not just the obvious events like rainstorms and wind, but also more subtle atmospheric phenomena. They noted the appearance and color of halos around the sun and moon, understanding that these optical effects often preceded changes in weather. They recorded the clarity or haziness of the atmosphere, the formation of clouds in particular patterns, and the direction from which winds arrived. What makes the Mesopotamian approach particularly fascinating is how they organized their observations into interpretive frameworks. They created extensive collections of weather omens, documents that connected atmospheric observations with predicted outcomes. These weren't merely superstitious pronouncements, but represented accumulated wisdom from generations of pattern recognition. If certain clouds appeared from a particular direction during a specific season, and rain typically followed within a certain time frame, this connection would be recorded and referenced for future predictions. The famous Enuma Anu Enlil, a massive series of tablets devoted to celestial and atmospheric omens, stands as testament to this systematic approach. Compiled over many centuries, this collection contained thousands of observations linking sky phenomena to earthly consequences. While modern science would not accept the causal relationships they proposed, the underlying observational rigor was genuine. They were attempting to find order in atmospheric chaos, to discover predictable patterns that could guide decision-making. The Assyrian king Ashurbanipal, ruling in the 7th century before the Common Era, maintained a magnificent library at Nineveh that included extensive collections of these astronomical and meteorological texts. His scribes didn't merely copy earlier tablets, but added new observations, corrections, and commentaries. This represented an evolving body of knowledge, refined across generations, with each era building upon the foundations laid by predecessors. Mesopotamian observers paid particular attention to optical phenomena in the atmosphere. They carefully described how the sun appeared at different times, noting when it seemed dim or when its rays appeared in unusual patterns. They tracked lunar halos with precision, understanding that rings around the moon often signaled approaching weather systems. The colors of sunrise and sunset were recorded, though their interpretations differed from our modern understanding of how atmospheric particles scatter light. Wind directions held special significance in their observations. They recognized that certain winds brought specific weather patterns, that the direction from which air arrived could predict what would follow. Desert winds from certain quarters brought dust and heat, while winds from other directions might carry moisture and the possibility of rain. They created terminology for different types of winds, categorizing them by origin, character, and the weather they heralded. The seasonal patterns of weather received careful documentation as well. Mesopotamian observers tracked how atmospheric conditions shifted through the year, noting when certain types of weather typically arrived and departed. They understood that seasons brought characteristic weather patterns, and deviations from these norms were worth recording. This seasonal awareness was essential for agricultural planning, helping farmers know when to plant and when to expect the rains that their crops required. Thunder and lightning captured their attention with particular intensity. These dramatic atmospheric phenomena seemed to bridge heaven and earth, and the observers recorded their occurrence with detailed notes about timing, location, and associated conditions. While they interpreted lightning through a different conceptual framework than modern science, their careful documentation of when and how these electrical discharges occurred represented genuine empirical observation. The Mesopotamian approach to weather observation also included attempts to quantify certain phenomena. While they lacked precision instruments, they developed descriptive scales for wind intensity, rainfall amount, and cloud coverage. A storm might be described in terms that conveyed its relative strength compared to typical storms. Rainfall could be characterized by its duration and apparent intensity. These qualitative assessments represented early attempts at standardization, allowing different observers to communicate about weather using common reference points. What distinguished the Mesopotamian weather watchers from casual observers was their commitment to systematic record-keeping over long time periods. Individual observations gained meaning when placed in context with observations from previous days, seasons, and years. Patterns emerged from accumulated data that wouldn't be visible in isolated observations. This long-term perspective allowed them to recognize cycles and anomalies, to notice when conditions departed from typical patterns. The clay tablets also reveal that weather information was shared and discussed among observers at different locations. Messages traveled along the rivers and trade routes, carrying news of atmospheric conditions in distant regions. This nascent information network, primitive by modern standards, represented an early recognition that weather wasn't merely a local phenomenon, but part of larger patterns extending across the landscape. As centuries passed and these tablets accumulated in libraries and archives, they formed a remarkable legacy. The Mesopotamian weather observers had created something unprecedented, a written record of the atmosphere's behavior extending across generations. Though their interpretive frameworks would eventually be superseded by different approaches to understanding weather, their commitment to careful observation and systematic documentation established principles that would echo through the history of meteorology. In the quiet scratching of stylus on clay, under the vast Mesopotamian sky, the foundation was being laid for humanity's long journey toward understanding the ever-changing atmosphere above. The warm Mediterranean sun cast long shadows across the gardens and porticos of ancient Athens as philosophers gathered to contemplate the nature of the world around them. While the Babylonians and Assyrians had meticulously recorded their observations of the heavens, the Greeks took a different approach to understanding the atmosphere. They sought not merely to document what happened in the sky, but to explain why it happened at all. Around 340 BCE, a brilliant mind named Aristotle sat down to compose what would become one of the most influential works on atmospheric phenomena ever written. He called it Meteorologica, from which our modern word meteorology derives. The Greek term meteora referred to things that existed high above the earth, suspended in the realm between the ground and the heavens. To Aristotle and his contemporaries, this included not just what we now call weather, but also comets, shooting stars, and various other celestial phenomena. Aristotle approached the atmosphere with the tools of natural philosophy, seeking to understand it through logic, observation, and systematic thought. He divided the space above the earth into distinct layers, each with its own characteristics and behaviors. The lowest layer, closest to the Earth's surface, was where most weather phenomena occurred. This was the realm of clouds, rain, wind, and storms. Above this, he proposed, lay progressively more refined and subtle regions, eventually transitioning into the unchanging perfection of the celestial sphere. In his contemplation of clouds, Aristotle theorized about their formation through processes he could observe and reason about. He understood that water from seas, rivers, and moist earth rose upward through the action of the sun's heat. This vapor, he proposed, ascended into the cooler regions of the atmosphere, where it condensed into the visible forms we see as clouds. When these clouds could no longer hold their accumulated moisture, rain fell back to earth, completing what he saw as a natural cycle. His explanation was remarkably close to our modern understanding of evaporation and condensation, though he lacked the detailed knowledge of molecular processes we possess today. Wind presented another puzzle for the Greek philosophers to unravel. Aristotle developed an elaborate theory about how different kinds of exhalations rose from the earth. The moist exhalations became clouds and rain, while dry exhalations moved horizontally, creating winds. He first recognized that winds came from specific directions and had different characteristics. Some were warm and dry, others cool and moist. He attempted to classify these winds, noting their seasonal patterns and their effects on weather conditions. The Greeks even had specific names for winds from different directions, treating them almost as individual personalities, each with its own temperament and influence. Thunder and lightning fascinated these ancient thinkers immensely. Aristotle proposed that thunder resulted from the collision and friction of clouds, or from dry exhalations trapped within clouds that ignited and burst forth violently. Lightning, in his view, was a sort of burning that occurred when these trapped exhalations caught fire. While his explanation seems quaint to modern understanding, he was attempting something revolutionary, explaining these dramatic phenomena through natural processes rather than attributing them solely to the actions of Zeus or other deities. The formation of dew, frost, and hail also captured Aristotle's attention. He observed that dew formed on cool, clear nights when moisture in the air condensed on surfaces, cooled by the night. Frost appeared when this process occurred at colder temperatures. Hail puzzled him more deeply, and his explanations for how water could freeze while falling through the air showed both the limits of his knowledge and the creativity of his reasoning. He proposed that hailstones formed in high, cold regions of the atmosphere and grew as they fell, occasionally being tossed upward again by powerful winds before finally descending to Earth. What made Aristotle's work so influential was not necessarily the accuracy of all his theories, but rather his systematic approach to atmospheric phenomena. He created a framework for thinking about weather as something that could be understood through careful observation and logical reasoning. His Meteorologica remained the foundational text on weather for nearly 2,000 years, studied and commented upon by scholars throughout the medieval period and into the Renaissance. Other Greek thinkers contributed their own observations and theories. Theophrastus, Aristotle's successor, wrote extensively about weather signs and prediction methods, collecting the accumulated folk wisdom of farmers, sailors, and travelers. His work on winds and weather signs represented a bridge between philosophical theory and practical observation. He documented how certain cloud formations preceded rain, how animal behavior changed before storms, and how the appearance of the sky at sunset could indicate the weather to come. The Greek approach to understanding the atmosphere established something profound in human thought: the idea that natural phenomena, including the seemingly capricious weather, followed consistent principles that human reason could comprehend. They moved weather observation from purely practical necessity or religious interpretation into the realm of systematic natural philosophy. Even though many of their specific theories would eventually be replaced by more accurate explanations, their fundamental assumption that weather could be understood through observation, reason, and systematic study laid crucial groundwork for all meteorology that would follow. As centuries passed, Aristotle's ideas about atmospheric layers, the water cycle, wind formation, and storm development spread throughout the Mediterranean world and beyond. Arabic scholars would later preserve and expand upon these Greek texts during Europe's medieval period, ensuring that this philosophical approach to weather understanding would eventually help kindle the scientific revolution. The Greeks had asked the essential questions and demonstrated that patient observation combined with logical reasoning could illuminate even the mysterious realm of clouds, winds, and storms that unfolded daily above them. Their legacy would shape how humanity approached the atmosphere for generations to come, even as new cultures and civilizations would add their own sophisticated understanding to the growing tapestry of meteorological knowledge. While Greek philosophers were developing their theories about the atmosphere in the Mediterranean world, halfway across the planet, other civilizations were building their own sophisticated understanding of weather through careful observation and deep cultural wisdom. In the vast landscapes of ancient China and across the diverse terrain of the Indian subcontinent, people were watching the sky with equal dedication, recording patterns that would shape their agricultural practices. philosophical traditions, and daily lives for millennia to come. In ancient China, weather observation became inseparable from the rhythms of agricultural life and the administrative concerns of the empire. Chinese scholars and officials maintained detailed records that stretched back into the mists of antiquity, creating an unbroken chain of weather documentation that would eventually span thousands of years. These were not casual observations scribbled in margins, but systematic recordings that officials were required to maintain as part of their duties to the emperor and the people. Rain, wind, frost, snow, and unusual atmospheric phenomena were all carefully noted, creating a treasury of meteorological data that modern scientists still study today. The Chinese developed a particularly keen understanding of wind patterns and their seasonal variations. They recognized that winds came from different directions at different times of year, and that these changing wind patterns brought predictable weather with them. Farmers learned to read the sky and the direction of the breeze, understanding that certain winds signaled the approach of rain, while others meant continued dry weather. This knowledge became embedded in agricultural calendars that guided planting and harvesting across the empire. One of the most remarkable aspects of Chinese weather knowledge was their early understanding of what we now call the monsoon cycle. They observed that massive seasonal shifts in wind direction brought dramatic changes in rainfall patterns, and they tracked these shifts with meticulous attention. The summer monsoon, bringing moisture-laden air from the south and east, was celebrated as the bringer of life-giving rain to the fields. The winter monsoon, with its cold, dry winds from the north and west, signaled a time of different agricultural activities and preparations for the coming year. Chinese scholars also developed sophisticated theories about the relationship between heaven and earth, between celestial patterns and atmospheric behavior. While these theories differed fundamentally from Greek approaches, they represented equally serious attempts to understand the forces that governed weather. The concept of qi, or vital energy, extended to explanations of atmospheric phenomena, with different types of qi thought to produce different weather conditions as they interacted and transformed. The Chinese made careful observations of clouds, recognizing different types and associating them with coming weather conditions. They documented optical phenomena like halos around the sun and moon, understanding these as signs of approaching changes. They tracked the arrival and departure of seasonal rains with precision that allowed them to develop increasingly reliable agricultural practices across diverse climate zones within their vast territory. Meanwhile, in India, another rich tradition of weather observation and understanding was developing within a very different cultural and environmental context. The Indian subcontinent's dramatic climate, with its intense monsoon seasons and stark contrasts between wet and dry periods, made weather observation a matter of fundamental importance to civilization itself. The arrival or failure of the monsoon rains could mean the difference between abundance and famine, and Indian scholars and farmers devoted tremendous attention to understanding and predicting these crucial atmospheric events. Ancient Indian texts contain detailed discussions of seasonal cycles, wind patterns, and rainfall. The division of the year into 6 seasons, rather than the 4 familiar in other traditions, reflected a more nuanced understanding of the region's climate patterns. Each season had its characteristic weather, its particular winds, and its role in the agricultural and spiritual cycles of life. These observations were woven into religious texts, astronomical treatises, and agricultural manuals, demonstrating how thoroughly weather knowledge permeated Indian intellectual life. Indian scholars developed theories about cloud formation, recognizing that clouds drew moisture from bodies of water and carried it across the land before releasing it as rain. They classified clouds into different types based on their appearance and the weather they brought, creating systems that helped observers predict coming conditions. The color, shape, and movement of clouds were all considered significant indicators, and skilled observers learned to read the sky with remarkable accuracy. The connection between wind and rain received particular attention in Indian meteorological thought. Scholars recognized that certain wind patterns preceded and accompanied the monsoon rains, and they developed elaborate descriptions of how different types of winds behaved. The arrival of moisture-laden winds from the ocean was understood as the herald of the rainy season, while shifts in wind direction marked transitions between seasons and weather patterns. Both Chinese and Indian civilizations also paid attention to long-term weather patterns and variations. Chinese records documented years of drought and flood, creating historical data sets that revealed patterns over decades and centuries. Indian texts discussed the variability of monsoons, recognizing that some years brought generous rains, while others saw scanty precipitation, and sought to identify signs that might predict whether a given year would be bountiful or difficult. The practical applications of this weather knowledge were enormous. Chinese farmers coordinated their planting with seasonal wind shifts and traditional weather indicators, while Indian agricultural practices were intimately tied to the monsoon cycle. Both civilizations developed extensive irrigation systems that reflected sophisticated understanding of rainfall patterns and water availability across different seasons. Trade and navigation also benefited from this accumulated weather wisdom. Chinese sailors learned to work with seasonal winds for coastal navigation, while Indian mariners became famous for their ability to harness monsoon winds for long-distance ocean voyages across the Indian Ocean. Arab traders would later learn from Indian navigators about the reliability of seasonal wind patterns, enabling extensive maritime trade networks that connected distant civilizations. The weather knowledge of ancient China and India represents parallel achievements in human understanding of the atmosphere. Developed independently from Mediterranean traditions, but equally systematic and sophisticated. These civilizations showed that careful, sustained observation, combined with theoretical framework, could yield practical understanding of weather patterns, even without the instruments that would later revolutionize meteorology. Their records and traditions would continue to inform weather understanding in Asia for centuries to come, creating foundations that persist in various forms even today. As night settles over these ancient lands in our imagination, we can picture generations of observers watching the sky, noting the winds, and accumulating the patient wisdom that would help their descendants navigate the ever-changing patterns of weather and season. As the medieval period settled across Europe like morning mist on a valley floor, the accumulated wisdom of ancient civilizations began to transform into something more immediate, more practical, more woven into the fabric of daily life. While scholars in monasteries preserved the philosophical writings of Aristotle and other classical thinkers, another kind of meteorological knowledge was flourishing in the fields, on the seas, and in the villages where ordinary people lived and worked. This was weather lore, the art of reading the sky through generations of careful observation, passed down in memorable phrases that could be recalled when dark clouds gathered or winds shifted direction. Red sky at night, shepherd's delight. Red sky in morning, shepherd's warning. These simple words, still familiar to us today, carry within them centuries of observation. The reddish hues that paint the evening sky result from sunlight passing through atmospheric particles, often indicating that dry, settled weather has moved in from the west, the direction from which most European weather arrives. A red morning sky, conversely, suggests that the fair weather has already passed eastward and moisture-laden clouds are approaching. Farmers and shepherds didn't understand the physics of light scattering, but they understood the pattern. They understood what followed. Medieval Europe was predominantly agricultural, and the success or failure of harvests meant the difference between prosperity and famine. Every person who worked the land became, by necessity, an amateur meteorologist. They watched for signs in the behavior of animals, in the appearance of the moon, in the feel of the wind against their skin. When cows lay down in pastures, rain was thought to be approaching. When swallows flew low, storms might follow. These observations weren't mere superstition. Many contained kernels of genuine correlation. Animals do respond to changes in atmospheric pressure. Birds do alter their flight patterns when air density changes before storms. The sailors of coastal communities developed their own extensive weather lore, for their lives depended even more critically on anticipating the moods of the atmosphere. Mackerel sky and mare's tails make tall ships carry low sails, they would say, referring to the rippled cirrocumulus clouds and wispy cirrus formations that often precede approaching weather fronts. These high ice crystal clouds frequently appear 12 to 24 hours before storms, giving mariners time to prepare. The sailors couldn't explain why these particular cloud formations preceded rough weather, but generations of observation had confirmed the connection reliably enough to guide decisions that meant survival or disaster. Along the coasts, fishermen learned to read the winds with exquisite precision. They gave names to different wind directions and associated each with particular weather characteristics. In the Mediterranean, the Mistral, Sirocco, and Levanta each brought distinctive conditions. In Britain, winds from the east brought cold, dry continental air, while western winds carried maritime moisture. These weren't abstract meteorological concepts, but intimate knowledge gained through lifetimes spent working outdoors, watching how the sky changed and what followed. The Christian calendar of medieval Europe, with its numerous saints' days, became a framework for organizing weather expectations throughout the year. If Saint Swithin's Day, the 15th of July, brought rain, folk wisdom held that 40 days of rain would follow. Such predictions had less to do with the saint himself than with the recognition that weather patterns in midsummer tended to persist once established. The 40-day period roughly corresponded to typical duration of summer weather regimes in the British Isles. The religious calendar simply provided memorable markers for seasonal weather transitions that people had long observed. Gardeners and farmers developed elaborate systems for predicting the severity of coming winters. They examined the thickness of onion skins, the abundance of berries on bushes, the early migration of birds. While many of these signs proved unreliable when tested systematically, they reflected a deep desire to forecast future conditions, to prepare for what the atmosphere might bring. In an age without meteorological instruments or forecasting services, these folk methods provided the only available guidance, however imperfect. Some weather lore contained remarkable sophistication. The practice of observing halos around the moon or sun to predict rain worked because these optical phenomena occur when thin, high cirrus clouds composed of ice crystals refract light, and these clouds frequently herald approaching fronts. "Ring around the moon, rain real soon," people would recite, encoding genuine meteorological insight into memorable verse. Similarly, the observation that pine cones close before rain reflected the physical reality that increasing humidity causes the scales to seal shut, protecting the seeds within. Medieval monasteries, with their emphasis on record-keeping and agricultural self-sufficiency, became repositories of weather observations. Monks noted unusual weather events in their chronicles: devastating storms, floods, droughts, and harsh winters. These records, kept over decades and sometimes centuries, created an invaluable historical archive. While not systematic scientific observations, they documented the climate variability of the period, including what historians now call the medieval warm period, and its eventual transition to cooler conditions. The Black Death and subsequent social upheavals of the 14th century disrupted many traditional patterns of knowledge transmission, yet weather lore persisted, perhaps because it remained so essential to survival. As feudal systems gradually evolved and trade expanded, the sharing of weather wisdom spread along merchant routes and shipping lanes. A saying useful in Flanders might travel to England. An observation made by Venetian sailors might reach the ears of Baltic fishermen. By the time the medieval period gave way to the Renaissance, Europe possessed a rich tapestry of weather lore, sometimes accurate, sometimes fanciful, but always reflecting humanity's relentless effort to understand and anticipate atmospheric behavior. This folk knowledge existed alongside, rather than in opposition to, the scholarly tradition preserved in universities and monasteries. Farmers reading the evening sky, and scholars reading Aristotle's Meteorologica, were both engaged in the same fundamental human endeavor, making sense of the ever-changing air above. This accumulated practical wisdom would soon meet a new force emerging across Europe, a spirit of systematic inquiry and experimentation that questioned inherited assumptions and sought to measure, quantify, and test. The instruments that would transform weather observation from art to science were beginning to take shape in the workshops of curious minds. Though the people reciting ancient weather proverbs in their fields and fishing boats could not yet imagine what was coming. The morning of a new age dawned slowly across Europe, as gradual and imperceptible as the changing of seasons themselves. After centuries of medieval traditions and accepted wisdom, a fresh wind began to blow through the corridors of learning. The Renaissance, that great flowering of human curiosity and creativity, turned its attention to everything under the sun, and indeed to the sun itself, and all the atmospheric wonders surrounding it. In the late 15th and early 16th centuries, a different kind of questioning emerged. Where medieval scholars had been content to consult ancient texts and accept the pronouncements of classical authorities, Renaissance thinkers began to ask a revolutionary question. what if we looked for ourselves? What if we measured, tested, and recorded what actually happens, rather than what we suppose should happen? This shift in thinking would prove as momentous for weather understanding as it was for every other branch of natural philosophy. The Italian city-states, wealthy from trade and alive with artistic and intellectual ferment, became laboratories of this new approach. In Florence, Venice, and Rome, educated men began to regard the atmosphere not as a realm of divine mystery beyond human comprehension, but as a physical domain that could be studied, understood, and perhaps even predicted. The same spirit that drove artists to study perspective and anatomy, that inspired architects to apply mathematical precision to their designs, now encouraged natural philosophers to examine the air around them with fresh eyes. Leonardo da Vinci, that most restlessly curious of Renaissance minds, turned his attention to atmospheric phenomena with characteristic thoroughness. Between his anatomical sketches and engineering designs, his notebooks filled with observations about clouds, wind, and rain. He watched how water vapor rose from heated surfaces, how clouds formed over mountains, how winds created waves on water. He recognized that wind was simply air in motion, flowing from areas of greater pressure to areas of lesser pressure, though he lacked the instruments to measure this pressure directly. His detailed drawings of cloud formations and his notes on their movements represented something new, a careful, systematic attempt to document atmospheric behavior without recourse to ancient authority or religious interpretation. In these same years, another shift occurred that would prove crucial to the development of meteorology. The great voyages of exploration, those daring journeys across previously uncharted oceans, brought back more than gold and spices. Sailors returned with detailed accounts of winds, currents, and weather patterns from distant seas. The Portuguese navigators, pushing ever farther down the coast of Africa and eventually around the Cape of Good Hope to India, compiled extensive knowledge of trade winds and monsoons. Spanish expeditions across the Atlantic discovered the reliable easterly winds of the tropics and the westerlies of higher latitudes. This practical knowledge, gathered through necessity and recorded in ship's logs and navigational guides, represented a vast new database of atmospheric behavior. The printing press, that transformative invention of the mid-15th century, accelerated the spread of both traditional weather lore and new observations. Books could now carry knowledge across borders and between generations with unprecedented fidelity. Weather observations made in one part of Europe could be read and compared with those from distant regions. Patterns began to emerge from this accumulated wisdom, though the theoretical framework to explain them remained elusive. As the 16th century progressed, the first tentative steps toward quantifying atmospheric phenomena began to appear. Natural philosophers recognized that to truly understand weather, they needed to measure it. Temperature, that fundamental property of air, remained frustratingly subjective. One person's warm was another's cool. Wind strength could be described as gentle or strong, but these terms meant different things to different observers. Rain could be called light or heavy, but without measurement, such descriptions conveyed only impressions. The challenge of measurement occupied some of the finest minds of the age. In Italy, members of the Accademia del Cimento, one of Europe's first scientific societies, founded in Florence in the mid-17th century, devoted themselves to experimental investigation of natural phenomena. They understood that progress required standardized observations, recorded with instruments rather than relying on human perception alone. Though the tools they needed did not yet exist, the recognition of their necessity marked a crucial step forward. This period also saw growing recognition that weather followed natural laws, even if those laws remained mysterious. If the planets moved in predictable paths according to mathematical principles, as Copernicus and later Kepler demonstrated, might not the atmosphere also operate according to discoverable rules? The success of astronomy in explaining celestial motions inspired hope that similar success might be achieved in understanding terrestrial phenomena. The intellectual climate of the Renaissance encouraged correspondence between scholars across Europe. Letters traveled between universities and courts, carrying observations, theories, and questions. A weather event witnessed in Prague might be described to a colleague in Paris, who would compare it with local conditions. Slowly, haltingly, a community of weather observers began to form, united not by institution or geography, but by shared curiosity about atmospheric behavior. Yet for all this growing interest, weather remained stubbornly unpredictable. The Renaissance mind could measure the movements of distant planets with increasing precision, could calculate the trajectory of a cannonball, could design buildings of unprecedented size and complexity. But whether tomorrow would bring rain or sunshine remained as uncertain as ever. The atmosphere guarded its secrets well, revealing only tantalizing glimpses of the patterns that governed its behavior. What the Renaissance provided was not answers, but something perhaps more valuable: the right questions and the beginnings of a method to pursue them. The idea that weather could be studied systematically, that measurements might reveal patterns invisible to casual observation, that understanding might come through patient accumulation of data rather than through appeals to ancient authority. These insights prepared the ground for the revolution that was coming. The stage was set for the next great leap forward. The intellectual framework existed. The motivation was strong. And across Europe, ingenious minds were beginning to wonder, could we build instruments to measure the invisible properties of air? The answer to that question would transform weather observation from an art of interpretation into a science of measurement, opening doors to understanding that had remained closed throughout all of human history until that moment. As the Renaissance spirit of inquiry continued to illuminate the natural world, a fundamental challenge remained for those who sought to understand the atmosphere. Weather had always been described in subjective terms: hot or cold, wet or dry, windy or calm. These descriptions varied from person to person, from place to place, and offered no common language for precise comparison. What one observer called quite warm, another might describe as moderately cool. This lack of precision hampered any systematic study of atmospheric phenomena. What was needed, though few fully realized it yet, were tools that could measure the invisible forces of nature with mathematical exactness. The transformation began quietly in the city of Padua, where Galileo Galilei had been teaching and conducting experiments. Around the year 1593, this brilliant mind turned his attention to measuring temperature. His device was ingeniously simple: a glass tube with a bulb at one end, inverted into a vessel of water. As the air in the bulb warmed, it expanded and pushed down on the water level in the tube. As it cooled, the water rose. Here was something revolutionary, a visible indicator of thermal change. Galileo's thermoscope, as it came to be known, had limitations. It responded not only to temperature, but also to atmospheric pressure, and it lacked any standardized scale. Yet it represented a profound conceptual breakthrough. Temperature, that most fundamental aspect of weather, could now be observed as a measurable quantity rather than a matter of personal sensation. Students and colleagues of Galileo refined this concept over the following decades. In Florence, members of the Accademia del Cimento, the Academy of Experiment, sealed liquid in glass tubes to eliminate the pressure problem, creating the first true thermometers. These instruments used various liquids: water, wine, even oil. Each had its advantages and drawbacks. The choice of liquid mattered less than the principle they embodied. Heat could be quantified, tracked, and compared across time and distance. The question of scale proved as important as the instrument itself. Without agreed-upon reference points, measurements remained merely relative. The Grand Duke of Tuscany's workshop produced thermometers marked with degrees, but these were calibrated using the temperature of the deepest wine cellars in Florence. Other instrument makers chose different standards. A reading of 10 degrees in Amsterdam meant something entirely different than in Paris or London. This confusion persisted until later decades, when natural fixed points, the freezing and boiling of water, would provide universal references. While the thermometer emerged from Galileo's circle in Italy, another crucial instrument had an origin story that began with a simple question about wells and pumps. In Florence, once again, around the year 1643, a young scientist named Evangelista Torricelli pondered a practical problem that had puzzled well diggers. Suction pumps could not draw water from depths greater than about 33 feet, regardless of how powerful the pump might be. Why should nature impose such a specific limit? Torricelli, who had been Galileo's assistant in the master's final years, approached the question with mathematical precision. He theorized that the atmosphere possessed weight, and that this weight pressing down on the surface of water in a well determined how high the water could be pushed up a pipe. Air, he proposed, was not weightless, but rather a fluid ocean pressing down upon everything at Earth's surface. To test this elegant hypothesis, he needed a substance much denser than water. Mercury, the strange liquid metal, would serve perfectly. The experiment was simplicity itself. Torricelli filled a glass tube about a yard long with mercury, sealed one end, and inverted it into a dish of mercury. The column of mercury in the tube fell, but did not empty completely. Instead, it settled at a height of about 30 inches, leaving an empty space at the sealed top of the tube. This space, the first human-created vacuum in recorded history, would later bear Torricelli's name. But more important for meteorology was what the experiment revealed. The height of the mercury column varied from day to day. The weight of the atmosphere was not constant. It fluctuated with weather patterns. Here was an invisible dimension of weather, made visible and measurable. Torricelli had created the barometer, though he did not live to see its full implications for weather observation. He died just 4 years after his breakthrough experiment, but his mercury column became the window through which scientists could observe atmospheric pressure. That fundamental force they had not known existed just decades before. News of Torricelli's experiment spread across Europe with the speed that important discoveries traveled in that era, through letters, visitors, and printed accounts. In France, the brilliant mathematician Blaise Pascal read of the Italians' work with immediate interest. If Torricelli was correct that air had weight, Pascal reasoned, then the atmosphere must be thinner at higher altitudes. There would simply be less air above to press down. In 1648, Pascal arranged an experiment of beautiful clarity. He asked his brother-in-law to carry a barometer up the steep slopes of the Puy de Dôme, a mountain in central France rising nearly 5,000 feet above the surrounding plains. As the climber ascended, he observed the mercury column at intervals. The results confirmed Pascal's prediction perfectly. The higher the elevation, the lower the mercury fell. The atmosphere did indeed have weight, and that weight decreased with altitude. Pascal's experiment transformed the barometer from a curiosity into a scientific instrument of the first importance. Observers soon noticed that barometric changes often preceded weather changes. A falling barometer frequently signaled approaching storms. A rising barometer suggested clearing skies. Here was something approaching prediction, though the mechanisms remained mysterious. The barometer became an essential tool for anyone seriously interested in weather, from natural philosophers to ship captains planning their voyages. The third great instrument of this remarkable century addressed another fundamental quality of air, its moisture content. The presence or absence of water vapor in the atmosphere determined comfort, influenced health, and related directly to the formation of clouds and precipitation. Yet humidity remained even more subjective than temperature in its assessment. The development of the hygrometer gave science a way to measure this elusive property. Various inventors contributed to hygrometry's development. Some used organic materials, human hair, wool, or plant fibers, that expanded and contracted with moisture. Others employed chemical substances that absorbed atmospheric moisture. The German scientist Otto von Guericke, better known for his dramatic experiments with air pumps and vacuum, developed a hygrometer using a pointer attached to materials sensitive to humidity. These early instruments were crude compared to what would come later, yet they represented the same conceptual revolution as the thermometer and barometer. Another invisible aspect of weather could now be rendered visible, measurable, and recordable. By the end of the 17th century, the careful observer possessed a remarkable toolkit. Temperature, atmospheric pressure, and humidity could all be measured with increasing precision. Wind direction had long been observable through vanes and flags. Rain could be collected and measured in gauges. The subjective experience of weather was giving way to objective measurement. Numbers were replacing adjectives. The weather on a particular day could now be described not as hot and stormy, but as 78 degrees with a barometric pressure of 29 inches and rising humidity. Descriptions that would mean the same thing to observers anywhere these instruments existed. This quantification of weather opened possibilities that would have seemed fantastic just a century before. With instruments providing standardized measurements, observers in different locations could meaningfully compare their readings. Patterns invisible to naked eye observation might emerge from systematic record-keeping. The path toward true weather science now lay open, awaiting those who would organize these measurements into networks of observation that spanned cities, nations, and eventually continents. The invention of instruments capable of measuring temperature, pressure, and humidity had transformed weather observation from an art of description into a practice of precision. Yet these wonderful new tools presented an unexpected challenge. A thermometer in London, a barometer in Paris, a weather vane in Amsterdam, each recorded its own local conditions with admirable accuracy. But what did these isolated measurements truly reveal about the atmosphere as a whole? The question that emerged in the minds of thoughtful observers was this: could weather truly be understood from a single vantage point? Or did its secrets lie in patterns that stretched across distances far greater than any one person could observe? The answer began to take shape in the middle decades of the 17th century, as scientists across Europe started to envision something remarkable: a network of observers, linked by correspondence and unified by common methods, who might together paint a broader picture of the atmosphere. The idea seemed almost audaciously ambitious. After all, communication between distant cities still depended upon letters carried by horseback or ship, and the very concept of coordinated scientific effort across international boundaries was still in its infancy. One of the first to pursue this vision was Ferdinand II, Grand Duke of Tuscany, whose genuine fascination with natural philosophy extended well beyond mere aristocratic patronage. In the year 1654, Ferdinand established what historians would later recognize as the world's first organized meteorological network, a system he called the Rete Meteorologica, or Meteorological Network. Under his sponsorship, standardized instruments were crafted in Florence by skilled artisans, thermometers sealed in glass, barometers of uniform design, and distributed to observers in cities throughout Italy and beyond. Stations were established in Florence, Cortigliano, Vallombrosa, Bologna, Parma, Milan, Innsbruck, Osnabrück, Paris, and even as far as Warsaw. Each location received identical instruments, carefully calibrated to ensure consistency. The observers, often scholars or members of religious orders with the education and discipline to maintain regular records, were given detailed instructions about when and how to make their measurements. 3 times each day, morning, afternoon, and evening, these scattered sentinels of science would note their readings, along with observations of wind direction, cloud conditions, and any notable atmospheric phenomena. The records were then dispatched by letter to Florence, where members of the Accademia del Cimento, the Academy of Experiments, would compile and compare them. For the first time in human history, it became possible to see weather not as a purely local phenomenon, but as something that varied systematically across space. When Florence experienced high pressure, what conditions prevailed in Paris? When storms swept through northern Italy, did similar disturbances appear in the records from Germany? The patterns were still obscure, the theories primitive, but the fundamental approach was sound. The Tuscan network operated for a decade, gathering a treasure trove of data before political and financial pressures led to its discontinuation in 1667. Yet the seed had been planted. The very existence of such an enterprise demonstrated that coordinated weather observation was feasible, and more importantly, that it could reveal insights impossible to glean from isolated measurements. As the decades rolled onward into the 18th century, the idea of weather networks found new champions. The Royal Society of London, that great forum for scientific exchange, established in 1660, became a clearinghouse for weather observations from across Britain and beyond. Fellows of the Society were encouraged to maintain weather journals and share their findings through letters read at meetings or published in the Society's philosophical transactions. Though less formally organized than the Tuscan network, this practice of sharing observations created an informal web of weather watchers throughout the British Isles. What these early networks began to reveal was both fascinating and humbling. The atmosphere, it seemed, was far more dynamic and interconnected than anyone had previously imagined. A change in wind direction observed in London might be followed a day later by similar changes reported from Edinburgh. Clear skies over the English Channel might coincide with storms in the North Sea. The weather was not a collection of isolated local events, but rather a vast, flowing, interconnected system. In Germany, the Societas Meteorologica Palatina, founded in Mannheim in 1780, would take the network concept to new heights of organization. Under the leadership of Johann Jakob Hemmer, this society established observation stations across Europe and even in North America and Greenland. Standardized instruments were distributed. Printed forms were created for recording observations in a uniform format, and the results were published in annual volumes. For 12 years, from 1781 to 1792, this network maintained remarkably consistent observations, creating one of the most valuable meteorological data sets of the 18th century. The observers in these networks were a diverse group: physicians, clergymen, teachers, estate managers. United by curiosity and a dedication to careful record-keeping, they rose at appointed hours to check their instruments, noted the sky conditions, measured rainfall in calibrated vessels, and faithfully recorded everything in their logs. Many maintained their observations for years, even decades, creating records that would prove invaluable to later researchers seeking to understand long-term weather patterns and climate variations. What made these networks possible was not merely the availability of instruments, but also the growing culture of scientific correspondence that flourished during the Enlightenment. Letters traveled constantly between natural philosophers, carrying news of discoveries, descriptions of experiments, and yes, reports of weather observations. The Republic of Letters, as this international community of scholars called itself, provided the social infrastructure that made collaborative science feasible, even in an age when the fastest communication still moved at the speed of a galloping horse. Yet for all their value, these early networks faced fundamental limitations. The greatest was time. Weather systems might move hundreds of miles in a day, but letters took days or weeks to traverse similar distances. By the time observations from distant stations reached a central location for compilation, the weather patterns they described had long since passed. The networks could reveal patterns retrospectively, helping to build understanding of how weather behaved, but they could not support real-time awareness of approaching systems. That capability would have to wait for a technology not yet invented: the electric telegraph. Still, as the 18th century drew toward its close, the foundation had been laid. The principle that weather must be observed across wide areas, that measurements must be standardized and systematic, that collaboration across distances could yield insights impossible to achieve in isolation. These ideas had taken root. The atmosphere was beginning to reveal itself, not as a mystery observed from single points, but as a unified, dynamic system whose behaviors played out across the face of the Earth. The patient observers at their scattered stations, checking their instruments at appointed hours and carefully noting each reading, were weaving together the first true picture of weather as a phenomenon that transcended local experience. As weather observation networks spread across Europe and scientists shared their daily measurements of temperature and humidity, a profound mystery remained at the heart of atmospheric science. What force drove the weather? What invisible mechanism caused storms to gather and winds to shift? The answer would emerge from a series of elegant experiments concerning the weight and pressure of the air itself. In the early 17th century, most natural philosophers still believed that air had no weight. It seemed logical enough. Air appeared to be nothing, an emptiness that existed between solid objects. Yet a few curious minds began to question this assumption, and in doing so, they would unlock one of meteorology's most fundamental secrets. The story truly begins in Florence, in the workshops and gardens of the Medici court, where practical problems sometimes led to theoretical breakthroughs. Well diggers had long known that suction pumps could not raise water higher than about 32 feet, no matter how perfect the seal or how strong the mechanism. The conventional explanation invoked nature's supposed horror of a vacuum, but this explanation seemed inadequate. Why would nature's horror have such a precise limit? Evangelista Torricelli, a mathematician and physicist who had studied with Galileo in the great scientist's final years, pondered this puzzle in 1643. Rather than trying to raise water to great heights, he conceived of a simpler experiment using mercury, a liquid nearly 14 times denser than water. If the principle was the same, mercury should rise to a proportionally lower height. Working with skilled glassblowers, Torricelli created a tube about 3 feet long, sealed at one end and open at the other. He filled this tube completely with mercury, then carefully inverted it into a bowl of mercury, keeping the open end submerged. The result was both beautiful and profound. The mercury column descended slightly, leaving an empty space at the top of the tube, but then it stabilized at a height of about 30 inches above the surface of the mercury in the bowl. This simple apparatus revealed something remarkable. The mercury was being held up not by any mystical force, but by the weight of the air pressing down on the surface of the mercury in the bowl. The empty space at the top of the tube was, Torricelli realized, very nearly a true vacuum. He had created the first barometer, though he did not yet know its meteorological significance. Torricelli noticed something else, something that would prove even more important for weather prediction. The height of the mercury column was not constant. On some days it stood slightly higher, on others it fell. These variations seemed random at first, but Torricelli began to suspect they might be connected to changes in the weather. Word of Torricelli's experiments traveled across Europe, reaching the brilliant young mathematician Blaise Pascal in Paris. Pascal, though often in poor health, possessed a restless intellect that seized upon Torricelli's discovery. If air had weight, Pascal reasoned, then there should be less air, and therefore less pressure, at higher altitudes. The weight of the atmosphere should diminish as one ascended a mountain. In 1648, Pascal arranged an elegant test of this hypothesis. being too unwell to climb mountains himself, he enlisted his brother-in-law, Florin Perrier, to carry a Torricellian tube up the Puy de Dôme, a mountain in central France, rising nearly 5,000 feet above sea level. Pascal requested careful measurements at various elevations, with a second barometer left at the base as a control. The results were unambiguous. As Perrier ascended the mountain, the mercury column dropped, settling at progressively lower heights. At the summit, the mercury stood more than 3 inches lower than at the base. When Perrier descended, the mercury rose again to its original height. The experiment demonstrated beyond doubt that atmospheric pressure decreased with altitude, confirming that the ocean of air surrounding Earth had definite physical properties, including weight and pressure, that varied with elevation. These experiments had immediate implications for understanding weather. Observers noticed that falling barometric pressure often preceded storms, while rising pressure suggested fair weather approaching. The barometer became a tool for prediction, though the reasons behind these correlations remain mysterious. Why should changing air pressure relate to clouds, rain, or wind? Meanwhile, in England, Robert Boyle conducted his own investigations into the nature of air. Using an improved air pump designed by his assistant Robert Hooke, Boyle performed experiments that revealed air's springiness, its tendency to expand when pressure decreased and compress when pressure increased. In 1662, Boyle published his famous law showing the inverse relationship between the pressure and volume of a gas at constant temperature. These discoveries gradually illuminated the connection between pressure and weather. Air masses with different pressures must move, flowing from areas of high pressure toward areas of low pressure, creating wind. Changes in pressure reflected the movements of vast invisible systems in the atmosphere. When pressure fell at a particular location, it suggested that a region of low pressure was approaching, often bringing clouds and precipitation. Rising pressure indicated an advancing area of high pressure, typically associated with clearing skies. The barometer transformed from a scientific curiosity into an indispensable tool for weather observation. By the late 17th century, careful observers maintained daily records of barometric pressure alongside temperature and humidity measurements. Patterns began to emerge from these records, patterns that suggested weather might eventually become predictable through systematic observation and understanding of atmospheric pressure systems. Edmund Halley, better known for the comet bearing his name, applied these insights to understanding winds. In 1686, he published the first meteorological chart showing trade wind patterns across the tropical oceans. Halley recognized that differences in air pressure created by unequal heating of Earth's surface drove these persistent wind systems. Warm air rising near the equator created regions of lower pressure, while cooler air descending in the subtropics created higher pressure. And air flowed between these regions in predictable patterns. The understanding of atmospheric pressure rippled through the scientific community, changing how natural philosophers thought about the air around them. The atmosphere was not merely empty space or an inert backdrop for weather phenomena. It was a dynamic, three-dimensional ocean of gas with measurable properties that followed physical laws. Pressure differences drove winds, influenced temperature, and played a central role in every aspect of weather. As the 18th century dawned, meteorology possessed its first truly quantitative tool for studying weather. The barometer gave observers a window into invisible atmospheric processes, revealing forces that shape the weather days before storms arrived or fair skies returned. Though much remained mysterious about how these pressure systems formed and moved, the foundation had been laid for genuine weather prediction based on physical understanding rather than folklore or speculation alone. As the 18th century progressed and the understanding of atmospheric pressure deepened across Europe, the spirit of scientific inquiry had crossed the Atlantic Ocean to the American colonies. There, among the many curious minds exploring the natural world, one figure would emerge whose contributions to meteorology would prove both practical and profound. Benjamin Franklin, a man already known for his inventions and writings, would turn his remarkable powers of observation toward the mysteries of storms and the electricity that crackled through the clouds above. Franklin's journey into meteorological understanding began not with grand theories, but with a simple moment of disappointment on an October evening in 1743. He had eagerly anticipated observing a lunar eclipse from his home in Philadelphia, only to find the sky obscured by an approaching storm system. The northeast wind drove clouds and rain across the city, making observation impossible. Later, through correspondence with his brother in Boston, Franklin learned something puzzling. The eclipse had been visible there, and the same storm that blocked Franklin's view did not arrive in Boston until several hours after it had struck Philadelphia. This was curious indeed, for the prevailing winds that evening had blown from the northeast, the very direction of Boston. How could a storm travel from Philadelphia toward Boston while the winds blew in the opposite direction? This observation lodged itself in Franklin's mind like a seed waiting to sprout. Over the following years, he gathered more accounts of storms, questioned ship captains about weather at sea, and collected observations from correspondents up and down the Atlantic coast. A pattern gradually revealed itself. The great storms that affected the American colonies moved in a general northeast direction along the coast, regardless of which way the local winds happened to blow at any given location. The realization was revolutionary in its simplicity. Storms were not merely local disturbances created by local winds. They were coherent systems, entities unto themselves that traveled across the landscape with their own internal circulation, carrying their winds with them as they moved. This insight represented a fundamental shift in how people conceived of weather. Previously, wind and storm had been thought of as essentially the same phenomenon, inseparable aspects of atmospheric disturbance. Franklin's observations suggested instead that storms were organized systems, moving independently, with winds that spiraled inward toward their centers. The wind you felt at any location was part of this larger circulation, a piece of a puzzle that extended far beyond what any single observer could see from one place. Franklin's meteorological interests, however, would become most famously associated with his experiments regarding atmospheric electricity. The phenomenon of lightning had fascinated and terrified humanity since the dawn of consciousness. Various explanations had been proposed, from divine intervention to the combustion of sulfurous vapors in the clouds. Franklin approached the question with characteristic practicality and ingenuity. He had already been experimenting with electricity in his laboratory, using Leyden jars to store electrical charge and studying the properties of this mysterious force. He noticed similarities between the sparks produced by his electrical apparatus and the lightning that flashed during thunderstorms. Both produced light and crackling sounds. Both seemed to prefer certain paths, particularly through metal conductors. Could they be the same phenomenon, merely different in scale? To test this hypothesis, Franklin proposed his famous kite experiment. On a stormy day in June of 1752, he flew a kite with a pointed wire attached to its top, with a metal key tied to the string near where he held it. The details of exactly how Franklin conducted this experiment have been debated by historians, and it is important to note that directly attracting a lightning strike would likely have been fatal. More probably, Franklin's kite drew ambient electrical charge from the storm clouds overhead, causing the fibers of the hemp string to stand on end and allowing him to draw sparks from the key. This demonstrated that clouds contained electrical charge, and that this charge could be drawn off and collected, just as it could be from his laboratory apparatus. The practical implications of this discovery were immediate and significant. If lightning was indeed electrical in nature, then the principles Franklin had discovered in his experiments could be applied to protect buildings. He developed the lightning rod, a pointed metal conductor extending above a structure and connected by wire to the ground. When lightning approached, it would preferentially strike the rod rather than the building itself, and the charge would be safely conducted into the earth. Franklin's lightning rods began appearing on buildings throughout the colonies and across Europe, representing perhaps one of the first practical applications of meteorological understanding to everyday safety. Franklin's contributions to meteorology extended beyond these famous experiments. He was among the first to propose the theory of convection currents in the atmosphere, understanding that air heated by the sun would rise, while cooler air would sink, creating circulation patterns. During his many Atlantic crossings, he carefully observed and documented ocean temperatures, ultimately producing one of the first maps of the Gulf Stream. He recognized that this current of warm water influenced weather patterns along the coast and could significantly affect sailing times. His suggestion that ship captains could use thermometers to navigate by tracking water temperature represented an early fusion of oceanography and meteorology. Throughout his investigations, Franklin demonstrated a methodology that would prove influential for future meteorologists. He combined careful observation with systematic record-keeping. He corresponded widely, gathering reports from many locations to understand phenomena across broader geographic areas. He moved fluidly between theory and practice, always seeking useful applications for scientific understanding. And he approached nature with a sense of wonder tempered by rational inquiry, believing that even the most mysterious phenomena could be understood through patient investigation. As Franklin aged, his meteorological observations continued. He noted the unusual cold summer that followed volcanic eruptions in Iceland, suspecting that dust in the atmosphere might be blocking sunlight, though he could not prove this connection definitively. He wondered about the nature of waterspouts and tornadoes, though these phenomena remained largely mysterious in his lifetime. His correspondence with other natural philosophers helped spread meteorological knowledge across the Atlantic, connecting American observations with European theories. The legacy of Franklin's work in meteorology rests not merely in specific discoveries, but in the spirit of inquiry he embodied. He demonstrated that weather was not beyond human understanding, that systematic observation could reveal patterns and principles, and that this understanding could be applied to practical benefit. His recognition that storms moved as coherent systems anticipated later developments in synoptic meteorology. His work on atmospheric electricity opened an entirely new field of investigation that continues to this day, and his example of methodical curiosity inspired generations of observers who would follow, each adding their piece to the growing mosaic of atmospheric understanding. As the 18th century drew to a close and a new century dawned, weather observation had become a well-established practice across the scientific world. Instruments measured temperature, pressure, and humidity with increasing precision. Networks of observers exchanged their findings through letters and scientific journals. Yet despite all these advances, when observers looked skyward and attempted to describe what they saw, confusion reigned. One person's description of a cloud bore little resemblance to another's account of seemingly the same formation. The sky above, ever-changing and infinitely varied, lacked a common vocabulary. Into this atmosphere of confusion stepped an unlikely revolutionary. Luke Howard was not a university professor or a gentleman scientist of independent means. He was a pharmacist in London, a member of the Society of Friends, whose fascination with the sky had begun in childhood. Born in 1772, Howard had watched clouds drift over the English countryside with the sort of patient attention that transforms casual observation into deep understanding. While preparing medicines in his shop, his mind often wandered to those ethereal forms that painted themselves across the heavens, constantly shifting, yet somehow following patterns he sensed but could not quite articulate. On a December evening in 1802, Howard stood before the Askesian Society, a small philosophical club that met in Plough Court, Lombard Street. The room was modest, lit by candlelight, filled with fellow seekers of natural knowledge. What Howard presented that evening would echo through the centuries, changing forever how humanity spoke about the sky. He proposed something elegantly simple yet profound. Clouds, despite their seemingly infinite variety, could be classified into a small number of basic categories, much as botanists had classified plants. Howard's system rested on a foundation of Latin names, giving clouds the dignity of scientific nomenclature. He identified three fundamental types, from which all other cloud forms derived. There was cumulus, meaning heap or pile, for those clouds that rose in distinct, separated masses, with flat bases and billowing tops like floating mountains of vapor. There was stratus, meaning layer, for those clouds that spread in horizontal sheets across the sky, often featureless and grey. And there was cirrus, meaning curl or wisp, for those high, delicate clouds that streaked across the upper atmosphere like brush strokes of white paint. But Howard understood that nature rarely presented pure forms. Clouds blended and combined, transitioned from one state to another. So he proposed compound categories. Cirrocumulus for those small white patches that rippled across high altitudes like scales on a fish. Cirrostratus for the thin, sheet-like veils that sometimes covered the entire sky at great heights. And cumulostratus, later renamed nimbus, for those dark, rain-bearing clouds that combined the massive vertical development of cumulus with the spreading character of stratus. The genius of Howard's classification lay not merely in naming, but in recognizing that these forms represented different atmospheric processes. A cumulus cloud spoke of rising air currents, of convection carrying moisture upward until it condensed into visible droplets. A stratus layer told of stable air, of moisture spread evenly across a broad region. Cirrus wisps revealed the frigid upper reaches of the atmosphere where water crystallized directly into ice. Each cloud type became a visible manifestation of invisible atmospheric dynamics. Howard's system spread across Europe with remarkable speed. Scientists and artists alike seized upon this new language for the sky. The Romantic poets, those celebrants of nature's grandeur, found in Howard's names a way to precisely invoke atmospheric moods. Johann Wolfgang von Goethe, the great German writer, was so moved by Howard's work that he composed poems in the Englishman's honor, celebrating how this London pharmacist had given humanity the words to speak of clouds. Before Howard, weather journals contained vague descriptions, cloudy with occasional breaks, or overcast with threatening aspect. After Howard, observers could write with precision, cumulus developing to cumulonimbus by afternoon, with cirrus appearing at higher elevations by evening. This precision enabled observers in different locations to compare notes meaningfully. A cumulus cloud over London was recognizably the same phenomenon as a cumulus cloud over Paris or Vienna, even if local conditions shaped its exact appearance. The classification system proved remarkably durable because it was based on observation rather than theory. Howard had not tried to force clouds into categories based on preconceived notions of how the atmosphere should behave. Instead, he had watched the sky patiently, noting which forms appeared repeatedly, which were truly distinct, and which were variations on common themes. This empirical approach gave his system a flexibility and practicality that more theoretical schemes lacked. As the 19th century progressed, meteorologists refined and expanded Howard's basic framework. They added new combination forms and subdivisions, recognizing gradations between his fundamental types. Altocumulus and altostratus emerged as mid-level clouds, distinct from their high cirrus cousins and low stratus relatives. Stratocumulus described those clouds that spread in layers but maintained individual puffy elements. Cumulonimbus became the official name for the towering thunderstorm clouds that reached from low altitudes to the boundaries of the troposphere. Howard's work represented something larger than cloud classification alone. It demonstrated how careful observation, systematic thinking, and clear nomenclature could bring order to natural phenomena that seemed chaotic. The same approach that had organized the plant kingdom, the animal kingdom, and the mineral kingdom could organize the transient forms of the atmosphere. Even phenomena as ephemeral as clouds could be understood, categorized and discussed with scientific precision. The London pharmacist's contribution reached far beyond meteorology. Artists studying his work began painting clouds with new attention to their structural differences. Landscape painters of the 19th century used Howard's categories to ensure their skies reflected real atmospheric conditions rather than artistic fancy. Photography, as it developed, captured cloud forms that could be definitively identified and studied, creating libraries of visual examples that illustrated Howard's types. Weather observers across the growing network of meteorological stations adopted Howard's terminology as their standard language. When telegraphs began connecting distant cities, enabling the rapid exchange of weather information, Howard's cloud classifications provided part of the vocabulary that made such exchanges meaningful. An observer could telegraph that cumulonimbus was approaching from the west, and recipients hundreds of miles away would understand precisely what sort of weather threatened. Luke Howard lived to see his classification system become the international standard for cloud description. He continued his pharmaceutical work, his weather observations, and his participation in London's scientific societies throughout a long life that extended into the 1860s. Yet his fame rested securely on those Latin names he had introduced one December evening at the dawn of the century, names that gave humanity a way to speak about the ever-changing gallery of forms that drifted across the sky, each one a visible sign of the atmosphere's invisible workings. With Luke Howard's cloud classifications now providing meteorologists a common vocabulary to describe what they saw overhead, scientists had gained the ability to communicate observations across distances with unprecedented precision. Yet describing clouds, recording temperatures, and noting wind directions at individual locations still left a critical question unanswered. How did all these scattered observations fit together into a larger picture? Weather, as Benjamin Franklin had demonstrated decades earlier, moved across the landscape. But what patterns governed these movements? What larger systems were at work? The key to unlocking these mysteries lay dormant, waiting for a technological innovation that would transform not just meteorology, but human communication itself. That innovation arrived in the 1840s with the electric telegraph, and it would revolutionize how humanity understood weather within a single remarkable decade. Before the telegraph, weather observations traveled only as fast as a horse could gallop or a ship could sail. A storm approaching from the west might be observed and recorded, but by the time news of it reached the next town, the storm itself had already arrived. Weather information always chased behind the weather itself, making prediction seem like an impossible dream. Meteorologists could study what had happened yesterday or last week, but they remained blind to what was happening right now across the broader landscape. The telegraph changed everything. Suddenly, observations made in distant cities could arrive within minutes rather than days. For the first time in human history, it became possible to know what the weather was doing in multiple places simultaneously. This seemingly simple capability opened entirely new ways of seeing the atmosphere. The first person to truly grasp the revolutionary potential of this simultaneous observation was James Pollard Espy in the United States, though he worked just before the telegraph became widespread. Espy had spent years studying storms and had become convinced that weather systems could be tracked and perhaps even predicted if only information could be gathered quickly enough. He advocated for a national system of weather observers, imagining a network that could follow storms across the continent. His vision was sound, but the technology of his time limited what could be achieved. The breakthrough came in 1849, when Joseph Henry, the first secretary of the Smithsonian Institution in Washington, established a network of telegraph stations across the United States specifically for weather observation. Henry equipped volunteer observers with standardized instruments and asked them to telegraph their readings to the Smithsonian each day. As reports arrived, Henry marked them on a large map of the United States hanging in the Smithsonian's main hall, using different colored discs to represent different weather conditions at each location. This map was not just a collection of isolated observations. When viewed as a whole, patterns emerged that no single observer could have seen. Areas of rain, regions of clear skies, zones of high or low pressure. These features became visible for the first time as coherent entities stretching across hundreds of miles. Weather was no longer a purely local phenomenon, but revealed itself as organized into vast systems that swept across the continent with recognizable structure and predictable behavior. Across the Atlantic, similar developments were unfolding. In Britain, the catastrophic loss of ships during the Crimean War, particularly during a violent storm in the Black Sea in November 1854, prompted calls for better understanding of weather patterns. The French astronomer Urbain Le Verrier investigated the storm and discovered that it had traveled across Europe, passing through areas where it had been observed and recorded. But those observations had not been shared quickly enough to provide warning to the doomed vessels. Had the telegraph been used to coordinate these observations, Le Verrier concluded, the disaster might have been prevented. This tragedy catalyzed the establishment of systematic weather observing networks across Europe. In 1855, France established a storm warning service. Britain followed in 1861 under the direction of Robert Fitzroy, the former captain of HMS Beagle who had carried Charles Darwin on his famous voyage decades earlier. Fitzroy, now an admiral and meteorologist, created a network of coastal stations that telegraphed observations to London twice daily. From these reports, Fitzroy prepared weather forecasts, a new word he coined, and storm warnings that were telegraphed back to ports where they were displayed for sailors and fishermen. But Fitzroy went further. He created synoptic charts, maps showing weather conditions across a wide area at a single moment in time. The word synoptic means seen together, and these charts did exactly that, presenting a simultaneous view of atmospheric conditions across Britain and surrounding waters. For the first time, weather was being visualized not as isolated events, but as interconnected systems with discernible patterns and structures. These early weather maps were relatively simple, showing wind direction, cloud cover, and barometric pressure readings at each observing station. Yet even in this basic form, they revealed something profound. Weather organized itself into recognizable features. Areas where barometric pressure was particularly low seemed to coincide with stormy conditions. Areas of high pressure brought fairer weather. And these pressure systems moved, often in predictable directions, carrying their associated weather along with them. The creation of synoptic weather maps marked a turning point in humanity's relationship with the atmosphere. No longer were meteorologists merely recording weather as passive observers. They were now seeing weather, truly seeing its large-scale structure and movement for the first time. It was as if a fog had lifted, revealing a landscape that had always been there but remained invisible until the right tools emerged to perceive it. Weather maps quickly became more sophisticated. Lines called isobars were drawn connecting points of equal atmospheric pressure, making pressure patterns immediately visible. These isobars often formed circular or oval patterns, the centers of high and low pressure systems that controlled weather across vast regions. Meteorologists noticed that winds tended to blow along these isobars, circling around pressure centers in characteristic ways. In the northern hemisphere, winds circled counterclockwise around low pressure areas and clockwise around highs, patterns that suggested deeper physical laws at work. As weather mapping became established practice in the 1860s and 1870s, meteorological services began publishing daily weather maps in newspapers, bringing this new way of visualizing the atmosphere to the general public. People could see for themselves the great sweeping patterns of high and low pressure, the fronts and systems that would come to define modern meteorology. Weather, once mysterious and capricious, was revealing its hidden order. The birth of weather maps represented more than just a new tool for meteorologists. It embodied a fundamental shift in how humanity understood the atmosphere, from a collection of local conditions to a global system of interacting patterns, flowing and evolving according to physical principles that were just beginning to come into focus. The stage was now set for the next great discoveries, understanding not just that patterns existed, but why they existed, what forces shaped them, and what fundamental motions drove the great circulation of winds around our turning planet. With weather maps now spreading across telegraph networks, revealing the grand sweep of storms and front moving across continents, meteorologists in the mid-19th century found themselves asking deeper questions. Why did the winds blow in the patterns they observed? What invisible forces guided the great rivers of air that flowed around the planet? The answers would come from patient observers scattered across the globe, and from theoretical minds willing to imagine the atmosphere as a single, unified system of motion. Sailors had long known about the trade winds, those remarkably consistent breezes that filled their sails in tropical latitudes, blowing steadily from the northeast in the northern hemisphere and from the southeast below the equator. These reliable winds had shaped exploration and commerce for centuries, carrying ships across oceans with predictable regularity. Yet why they blew with such consistency, always from the same general direction in the same regions, remained a puzzle that begged for explanation. The first person to propose a comprehensive theory was George Hadley, an English physicist and meteorologist, who, in 1735, presented a paper to the Royal Society with a deceptively simple idea. Hadley reasoned that the sun heated the equatorial regions more intensely than the poles. This warm air, being less dense, would rise. Meanwhile, cooler air from higher latitudes would flow toward the equator to replace it, creating a circulation. The rising warm air would then flow toward the poles at higher altitudes, cool, sink, and return toward the equator near the surface. The beauty of Hadley's model lay in its elegant simplicity, but he added one crucial insight that elevated his theory beyond the obvious. He recognized that Earth itself was rotating, and that this rotation would affect the moving air. As air flowed from the tropics toward the poles, or from the poles toward the equator, it would be deflected by Earth's rotation. This deflection, he suggested, explained why the trade winds didn't blow directly north and south, but came from an easterly direction instead. For more than a century, Hadley's ideas remained largely theoretical curiosities, discussed among natural philosophers, but not fully developed. Then, in the mid-1800s, an American scientist named William Ferrel took up the challenge of understanding atmospheric circulation more completely. Ferrel was a schoolteacher from Tennessee who became fascinated by the motions of the atmosphere and ocean. Working in relative isolation, he developed mathematical descriptions of how Earth's rotation influenced moving fluids. Ferrel explained what came to be called the Coriolis effect, named after the French mathematician Gaspard Gustave de Coriolis, who had described the mathematics of motion in rotating systems. As air moved across Earth's surface, the rotation beneath it caused an apparent deflection. In the northern hemisphere, moving air curved to the right of its initial direction. In the southern hemisphere, it curved to the left. This wasn't because any force pushed the air sideways, but rather because the ground beneath was constantly turning. This insight revolutionized understanding of wind patterns. Ferrel proposed that Earth's atmosphere didn't have just one large circulation cell in each hemisphere, as Hadley had suggested, but three distinct cells. The Hadley cell operated in the tropics, with air rising at the equator, flowing poleward at altitude, then sinking in the subtropics around 30 degrees latitude and returning toward the equator as the trade winds. But there were two additional circulation patterns in higher latitudes. Between 30 and 60 degrees latitude, Ferrel described a middle cell where surface winds blew toward the poles, picking up moisture from the oceans and bringing changeable weather to temperate regions. These were the prevailing westerlies that dominated weather in places like Europe and the northern United States. Finally, in polar regions, a third cell featured cold, dense air sinking over the poles and flowing toward lower latitudes before being deflected eastward. The picture that emerged was one of remarkable organization. The atmosphere wasn't moving chaotically, but in great, predictable patterns dictated by solar heating and Earth's rotation. The intertropical convergence zone, where trade winds from both hemispheres met near the equator, became recognized as a region of ascending air and frequent thunderstorms. The subtropical highs, where air descended after its journey from the equator, were zones of dry, stable weather, explaining the location of many of Earth's great deserts. Matthew Fontaine, Maury, a United States Navy officer who became superintendent of the Depot of Charts and Instruments, made crucial contributions by compiling vast amounts of ship observations into wind and current charts. His wind and current maps, published in the 1850s, revealed patterns that confirmed the theoretical circulation models. Maury's work had immediate practical value, allowing ships to plan routes that took advantage of favorable winds and currents, dramatically reducing voyage times. As understanding grew, meteorologists recognized that the jet streams, those swift rivers of air in the upper atmosphere that had puzzled earlier observers, were related to the boundaries between these circulation cells, where warm tropical air masses met colder polar air in middle latitudes. The temperature contrast created powerful westerly winds aloft. These jet streams, flowing at altitudes where weather balloons would later venture, steered the movement of surface weather systems below. The realization that local winds were part of global patterns connected weather observation stations separated by vast distances. A change in pressure in one location might signal the approach of a wind shift that was part of a larger circulation. The atmosphere began to reveal itself as a single interconnected fluid envelope wrapping Earth, with motions at every scale influenced by the fundamental drivers of solar heating and planetary rotation. Monsoons, those dramatic seasonal wind reversals that brought life-giving rains to India and other tropical regions, could now be understood as manifestations of the same principles operating on continental scales. As land masses heated more rapidly than oceans during summer, the temperature contrast drove moisture-laden winds inland. During winter, the pattern reversed. The age-old phenomenon that had governed agriculture and civilization for millennia had a physical explanation rooted in the same atmospheric dynamics that shaped trade winds and westerlies. By the late 19th century, the fundamental patterns of global atmospheric circulation had been mapped and explained. What remained mysterious to those earlier scientists was how much more complexity would be revealed when instruments could probe the upper atmosphere directly, when mathematics could calculate the detailed motions, and when satellites could watch the swirling patterns from space. But the essential framework had been established through careful reasoning, patient observation, and the willingness to imagine Earth's atmosphere as a dynamic, rotating system responding to the ancient rhythm of sunlight falling unevenly on a spinning sphere. With the understanding of how winds circulate around our globe established, scientists of the 19th century turned their attention to the most dramatic and violent expressions of atmospheric power. The gentle breezes that guided sailing ships and the predictable trade winds were one thing, but the furious tempests that could devastate coastlines and the whirling vortices that appeared from nowhere to destroy everything in their path demanded explanation. These storms had terrified and fascinated humanity since the beginning of recorded history, but now, for the first time, observers possessed the tools and the conceptual framework to study them systematically. The great tropical cyclones that formed over warm ocean waters had long been known by different names in different parts of the world. Caribbean sailors called them hurricanes, a word derived from the indigenous Taino people's storm god. In the Western Pacific, they were typhoons. In the Indian Ocean, simply cyclones. But whatever name they carried, these massive rotating storms represented nature's most powerful atmospheric phenomena, and understanding them became a priority for meteorologists whose nations depended on maritime trade and coastal settlements. William Redfield, an American saddlemaker and self-taught scientist, made a crucial observation following a powerful hurricane that struck the northeastern United States in September of 1821. Traveling from his home in Connecticut to Massachusetts shortly after the storm, Redfield noticed something peculiar about the fallen trees. In Connecticut, they had fallen toward the northwest. In Massachusetts, they had fallen toward the southeast. This pattern suggested something remarkable. The winds had been blowing in opposite directions in locations not far apart. Redfield spent years collecting similar observations from ship's logs and eyewitness accounts, gradually building evidence that hurricanes were rotating systems of wind, not straight-line blasts of air as had been commonly assumed. Meanwhile, James Espy, a schoolteacher turned meteorologist, was developing a different theory of storms. Espy focused on the role of rising air and condensation, arguing that the release of heat when water vapor condenses into droplets provided the energy that powered storms. He conducted careful experiments, creating artificial clouds in laboratory apparatus, and observed how air naturally moves inward and upward when heated. Espy believed that all storms were fundamentally convective phenomena, driven by this upward motion of warm, moist air. The debate between Redfield's rotational theory and Espy's convection theory became one of the great scientific controversies of mid-19th century American science. Both men were partly correct, as later investigators would demonstrate. Hurricanes do indeed rotate, as Redfield had shown, but they are also powered by the convective release of heat from condensing water vapor, as Espy had theorized. The complete picture required understanding how these processes work together, how the rotation of the Earth itself influenced the spinning motion, and how the ocean's warm waters provided the fuel for these atmospheric engines. Henry Piddington, a British sea captain and later curator of a museum in Calcutta, made significant contributions to understanding tropical cyclones through his analysis of ship's logs from vessels caught in these storms. He coined the term cyclone in 1848 from the Greek word for coil to describe these rotating systems. More importantly, Piddington developed practical rules for mariners to determine their position relative to a cyclone's center and to take appropriate action to avoid the most dangerous portions of the storm. His handbook became essential reading for sailors navigating tropical waters. On land, different storms presented different mysteries. Tornadoes, those violently rotating columns of air extending from thunderstorms to the ground, were rarer than hurricanes, but even more intense in their immediate vicinity. Reports of tornadoes throughout history had often verged on the fantastical, and even scientists were uncertain about their true nature. Were they electrical phenomena? Were they caused by the meeting of different air currents? Did they descend from clouds or rise from the ground? John Park Finley, a young officer in the United States Army Signal Corps, conducted the first systematic study of tornadoes beginning in the 1870s. Finley traveled to tornado-damaged paths, interviewed witnesses, and carefully documented the width, length, and characteristics of tornado tracks across the landscape. He collected hundreds of reports and began to discern patterns in when and where tornadoes occurred. Finley recognized that tornadoes were associated with particular types of thunderstorms, and that certain atmospheric conditions made their formation more likely. The structure of thunderstorms themselves gradually came into focus during this period. Observers noted that severe thunderstorms often exhibited a characteristic anvil shape at their tops, where rising air spread out against the stable stratosphere. They recognized that lightning and thunder were electrical phenomena, though the exact mechanisms remained mysterious. They understood that hail required powerful updrafts to keep ice particles aloft long enough to grow large, and that the strongest updrafts produced the largest hailstones. European meteorologists, meanwhile, were developing sophisticated observations of winter storms and the low-pressure systems that brought rain and wind to the continent. These extratropical cyclones, though less violent than their tropical cousins, were the weather makers that most affected daily life in the temperate latitudes. Scientists traced how these systems formed, matured, and eventually dissipated, noting the characteristic patterns of wind shift, pressure fall and rise, and precipitation that accompanied their passage. The role of atmospheric instability in storm formation became clearer through careful observation and theoretical work. When warm, moist air near the surface was topped by cooler, drier air above, the atmosphere was poised for convection. Any trigger, any slight lifting of the surface air, could release this instability like a spring, causing air to rush upward and storms to develop with remarkable speed. Understanding this instability helped explain why some days produced violent weather, while others, seemingly similar, remained calm. By the latter decades of the 19th century, the basic life cycles of various storm types were becoming understood. Scientists could describe how a tropical cyclone organized itself around a warm core of rising air, how it drew energy from warm ocean waters, and how it weakened upon moving over land. They could explain how winter storms formed along the boundaries between different air masses, intensifying as they drew on the temperature contrasts. They could identify the atmospheric patterns that favored tornado development, even if they could not yet predict individual tornadoes with any reliability. This growing understanding of storms represented more than scientific curiosity. These violent atmospheric events killed thousands of people and destroyed property worth millions. Being able to recognize when conditions favored storm development, to track storms as they moved, and to warn populations in their path would save lives and livelihoods. The science of storms was becoming the foundation for the possibility of useful forecasting, the subject that would preoccupy meteorologists as the 20th century approached. The mid-19th century brought with it a profound shift in humanity's relationship with the weather. For thousands of years, people had observed, recorded, and theorized about atmospheric phenomena, but prediction remained elusive, tantalizingly out of reach. Now, with telegraph wires stretching across continents and networks of observers recording simultaneous measurements, the dream of forecasting weather began to transform from fantasy into reality. The establishment of government weather services marked a turning point in this journey. In 1854, the British government appointed Robert Fitzroy as head of a new meteorological department within the Board of Trade. Fitzroy, who had previously commanded the HMS Beagle during Charles Darwin's famous voyage, brought both his naval experience and his passionate belief that meteorology could save lives at sea. He understood viscerally how sudden storms could devastate ships and crews, and he dedicated himself to creating a system that might provide warning before disaster struck. Fitzroy envisioned a network of coastal stations that would telegraph their observations to a central office in London. From these reports, he believed patterns could be discerned and predictions made. It was an ambitious undertaking, requiring not just scientific insight, but also administrative skill, political support, and the willingness to stake one's reputation on forecasts that might prove incorrect. The atmosphere, after all, was not a mechanical device that operated with perfect regularity. It was dynamic, complex, and often surprising. In 1861, Fitzroy published his first storm warnings, simple alerts sent by telegraph to coastal ports when barometric readings and other observations suggested dangerous weather approaching. These warnings were cautious at first, focusing on immediate threats rather than extended predictions. But Fitzroy's ambitions grew. By 1860, he began issuing what he called forecasts, predictions of weather conditions for the day ahead. These appeared in newspapers, available for all to read, marking the first time in human history that weather predictions became a public service, freely distributed to anyone who might benefit from them. The reception was mixed. Some forecasts proved remarkably accurate, earning Fitzroy praise and gratitude, particularly from sailors who adjusted their plans based on his warnings. But the atmosphere revealed its complexity through failures as well. Predicted storms sometimes veered off course or dissipated unexpectedly. Fair weather forecasts occasionally gave way to rain and wind. Critics emerged, questioning whether accurate prediction was truly possible, whether Fitzroy was overstepping the bounds of what science could achieve. The criticism weighed heavily on Fitzroy, who felt personally responsible for each incorrect forecast. He refined his methods continually, studying failures as intently as successes, seeking patterns in the seemingly chaotic flow of weather systems across the British Isles. He developed elaborate tables and rules, attempting to codify the relationships between pressure, wind, temperature, and moisture that governed atmospheric behavior. Yet despite his dedication, perfect accuracy remained beyond reach. The newspapers that had celebrated his early successes began to mock his errors, and some in the scientific establishment questioned whether forecasting should be attempted at all. Across the Atlantic Ocean, similar efforts were unfolding. The United States established the Division of Telegrams and Reports for the Benefit of Commerce in 1870, which would later become the Weather Bureau. Under the direction of Cleveland Abbey, who earned the affectionate nickname Old Probabilities for his weather predictions, American meteorologists began issuing forecasts based on telegraph reports from observers scattered across the growing nation. Abbey approached forecasting with scientific rigor, acknowledging uncertainty and expressing predictions in terms of probability rather than certainty. His humble approach earned respect, even when forecasts proved incorrect. The American system benefited from the continent's geography. Weather systems typically moved from west to east, and observations from western stations could provide advance warning of approaching conditions. This westward lookout gave American forecasters a natural advantage, a window into the future that European forecasters, surrounded by ocean, could only partially enjoy. Nevertheless, forecasting remained challenging. Storms intensified or weakened unpredictably, their paths curving north or south in response to atmospheric patterns that observers could only partially glimpse. In France, Urbain Le Verrier established a meteorological warning service following a devastating storm in 1854 that destroyed much of the French fleet during the Crimean War. Investigations revealed that the storm had moved across Europe in a predictable pattern, visible in retrospective analysis of pressure readings from various locations. Had those readings been available simultaneously through telegraph, warnings could have been issued and ships kept safely in harbor. This realization spurred Le Verrier, an astronomer famous for mathematically predicting the existence of Neptune, to create a network of observing stations connected by telegraph. Within years, France was issuing storm warnings based on real-time observations. These early forecasting services shared common challenges. Observations remained sparse, with vast regions of ocean and land producing no data at all. The upper atmosphere remained almost entirely unknown, its winds and temperatures unmeasured. Forecasters worked with surface observations alone, trying to infer three-dimensional atmospheric structure from two-dimensional patterns. They developed rules of thumb, empirical relationships between observable conditions and subsequent weather. But these rules had exceptions, situations where the usual patterns failed to hold. Despite these limitations, forecasting gradually improved through the late 19th century. Forecasters learned from experience, recognizing subtle patterns that distinguish dangerous storms from ordinary weather systems. They shared knowledge across borders, comparing techniques and observations. International conferences brought meteorologists together to standardize instruments, observation times, and terminology. A global community of weather observers and forecasters emerged, united by the common goal of understanding and predicting the atmosphere's behavior. The public's relationship with weather forecasts evolved during this period as well. Initial skepticism gave way to cautious acceptance, as forecasts proved useful often enough to justify attention. Farmers consulted forecasts when planning harvests, travelers when scheduling journeys, sailors when deciding whether to leave port. The forecasts were far from perfect, but they were better than nothing. Better than relying solely on folklore and yesterday's weather to guess tomorrow's conditions. By century's end, weather forecasting had established itself as a legitimate government function in many nations. It had survived its early controversies and proven its value despite inevitable errors. The forecasters themselves had developed a clearer sense of what was possible and what remained beyond current capabilities. Short-range predictions looking ahead hours or perhaps a day showed definite skill. Longer predictions remained speculative, dependent on atmospheric patterns that could shift unexpectedly. Yet the foundation had been laid. Weather prediction, once the realm of folklore and superstition, had become a scientific endeavor. Imperfect, but genuine, a service that saved lives and aided commerce. The age of forecasting had truly begun, and with it, humanity's ability to prepare for the weather rather than simply endure it. As forecasters gained confidence in predicting tomorrow's weather, from observations gathered across the surface of the Earth, a profound question lingered in the minds of meteorologists as the 19th century drew to a close. What was happening above their heads? The weather they observed and measured existed not on a flat plain, but in a three-dimensional ocean of air that extended upward into mysteries yet unexplored. The atmosphere, they realized, was not simply a thin layer clinging to the ground, but a vast vertical realm that held secrets essential to understanding the winds, storms, and changing conditions below. The desire to probe the upper air was as old as human curiosity itself, but practical means to do so emerged gradually. In the early days of this exploration, some scientists turned to mountains, climbing to high elevations where the air grew thin and cold. Observatory stations were established on peaks across Europe and America, where dedicated observers endured harsh conditions to record temperature, pressure, and wind at altitudes beyond the reach of valley dwellers. Yet mountains, while useful, were stationary and limited. The atmosphere demanded a more flexible approach. Kites offered an ingenious solution. By the late 19th century, meteorologists were launching specially designed kites, carrying small instrument packages high into the sky. These weren't the simple toys of childhood, but robust constructions, capable of reaching remarkable heights when flown in teams or trains. The instruments they carried were ingeniously crafted to record temperature and humidity on charts that could be retrieved when the kites were reeled back to Earth. On favorable days, these kite trains could reach altitudes of several thousand feet, sending back their silent reports about conditions in the previously inaccessible air above. The truly transformative tool for atmospheric exploration, however, was the balloon. Hydrogen and hot air balloons had captured human imagination since the flights of the Montgolfier brothers, more than a century earlier. But their application to scientific investigation required both courage and careful instrumentation. In the 1890s, meteorologists began sending unmanned balloons aloft, carrying self-recording instruments. These free-flying balloons would drift with the winds, climbing to astonishing heights before their instruments eventually returned to Earth, often far from their launch points. The patient work of recovering these instruments and analyzing their traces revealed an atmosphere far more complex than anyone had imagined. French meteorologist Léon Tisserand de Boer devoted years to these balloon soundings, launching hundreds of instruments from his private observatory. What he discovered through this painstaking work changed the understanding of atmospheric structure forever. His instruments consistently showed that temperature decreased with altitude as expected, but only up to a certain height, approximately 11 kilometers above the surface. Beyond that boundary, temperature stopped falling and even began to increase. This was unexpected, contradicting the assumption that the atmosphere simply grew colder and colder as one ascended towards space. In 1902, Thysserance de Boer announced his discovery of what he termed the stratosphere, a layer of air fundamentally different from the turbulent lower atmosphere. Below this stable layer lay what would come to be called the troposphere, from the Greek word for turning or changing, where all weather occurred. This revelation that the atmosphere had distinct layers, each with its own characteristics, provided a framework for understanding atmospheric behavior that had been missing. The boundary between these layers, the tropopause, marked the ceiling of weather as humans experienced it. Simultaneously, German scientists were conducting similar explorations with equally remarkable results. Richard Assmann, working independently, also identified this stratified structure of the atmosphere. His careful observations using kites and balloons confirmed that the upper air was not merely a continuation of surface conditions at greater heights, but a distinct realm governed by different processes. The convergence of these independent discoveries lent credence to this new understanding of atmospheric architecture. The early 20th century saw continued refinement of upper air exploration. Manned balloon ascents, though dangerous, provided valuable observations as brave aeronauts climbed to record-breaking heights, enduring extreme cold and thin air to record their observations directly. These flights revealed the powerful rivers of wind that flowed in the upper troposphere, swift currents that moved far faster than any wind experienced at the surface. Though these high-altitude winds had been theorized, their actual strength and consistency surprised observers. The development of the radio sonde in the 1920s and 1930s represented another leap forward in atmospheric exploration. This ingenious device combined meteorological instruments with a small radio transmitter, allowing it to broadcast measurements in real time as it ascended beneath a balloon. No longer was it necessary to recover instruments to learn what they had recorded. Instead, ground stations could receive continuous streams of data showing temperature, humidity, and pressure at precisely known altitudes as the radio sonde climbed through the atmosphere. This innovation transformed upper air observation from an occasional research activity into a routine operational tool. By the 1930s, networks of radio sonde stations were being established across many nations. Twice daily launches, typically at midnight and noon, began providing regular profiles of the atmosphere's vertical structure. These soundings revealed that weather systems extended upward through great depths of the atmosphere, that storms had vertical structures as important as their horizontal dimensions, and that conditions thousands of feet above the ground could influence surface weather hours or days later. The discovery of the jet stream stands as one of the most significant findings of upper air exploration. Japanese meteorologist Wasaburo Oishi had documented powerful high-altitude winds in the 1920s, but his work, published in Esperanto, went largely unnoticed by Western scientists. During World War II, American bomber crews flying at high altitudes over the Pacific encountered fierce headwinds and unexpected tailwinds that sometimes exceeded 200 miles per hour. These experiences brought focused attention to the narrow bands of extremely fast-moving air that snaked through the upper troposphere. After the war, meteorologists recognized that these jet streams were fundamental features of atmospheric circulation, marking boundaries between different air masses and steering weather systems across continents and oceans. The jets meandered northward and southward, accelerating and decelerating, and their position and strength influenced weather patterns at the surface in profound ways. Understanding the jet stream became essential for weather forecasting, and its discovery illustrated how much remained hidden until scientists could observe the upper atmosphere systematically. The exploration of the upper air revealed that the atmosphere was not a uniform blanket of gas, but a dynamic, layered system with its own geography. Temperature inversions, stable layers, zones of wind shear, and regions of moisture existed at various altitudes, each playing a role in the development and movement of weather systems. Forecasters now had to think in 3 dimensions, considering not just what was happening across the map, but what was occurring throughout the vertical column of air above each location. As the 20th century progressed, upper air data became indispensable for weather prediction. The twice-daily balloon launches continued, building a climatology of the upper atmosphere that revealed seasonal patterns, regional characteristics, and the ways that conditions aloft varied with different weather situations. This vertical perspective transformed meteorology from a surface-based science into one that embraced the full depth of the troposphere, setting the stage for even more sophisticated approaches that would emerge as mathematical and computational tools advanced. As the 20th century dawned, meteorology stood at a threshold. Weather observers had amassed decades of data from around the world. They had mapped storms, classified clouds, and sent instruments soaring into the upper atmosphere. Yet despite this wealth of observation, weather prediction remained frustratingly imprecise, more craft than science, dependent on the experienced eye of individual forecasters who relied heavily on intuition and pattern recognition. What meteorology lacked was a unifying framework, a mathematical foundation that could transform these countless observations into reliable predictions. Into this landscape stepped a Norwegian physicist named Wilhelm Bjerknes, whose vision would reshape meteorology from a descriptive endeavor into a rigorous physical science. Born in Oslo in 1862, Bjerknes had spent his early career studying fluid dynamics and thermodynamics, seemingly far removed from the practical concerns of weather forecasting. But in 1904, he published a revolutionary paper that would change everything. Bjerknes proposed that weather prediction could be treated as a problem of physics and mathematics, governed by fundamental equations describing how air moved, how temperature changed, and how pressure systems evolved. If one knew the current state of the atmosphere with sufficient precision, Bjerknes argued, one could calculate its future state using these physical laws. This idea, simple in concept, but staggering in its implications, suggested that weather forecasting need not rely on empirical rules and local experience alone. Instead, it could become a matter of solving equations, of calculating the atmosphere's future from its present conditions. Bjerknes called this approach dynamic meteorology, and he dedicated the remainder of his career to making it practical. The opportunity to test and develop these ideas came during the First World War, when Bjerknes relocated to Bergen, Norway. There, Sheltered from the conflict that engulfed Europe, he established what would become known as the Bergen School of Meteorology. Gathered around him was a remarkable group of young scientists, including his son Jakob Bjerknes, along with Halvor Solberg and Tor Bergeron. Together, they would develop the conceptual models and analytical techniques that still form the backbone of weather analysis today. Norway's wartime isolation meant that weather reports from the Atlantic had ceased, yet accurate forecasts remained crucial for fishing fleets and shipping. The Bergen team addressed this challenge by establishing a dense network of observation stations across southern Norway. Stations positioned close enough together that they could capture weather changes in remarkable detail. The data flowing in from these stations revealed patterns that previous, more widely spaced observations had missed entirely. As the Bergen team analyzed their detailed weather maps, they began to perceive the atmosphere not as a gradual continuum, but as organized into distinct air masses. Vast bodies of air with relatively uniform temperature and moisture characteristics. They observed that between these air masses lay sharp boundaries where conditions changed dramatically over short distances. These boundaries appeared as lines on weather maps where winds shifted direction, where temperatures dropped suddenly, where clouds and precipitation formed with remarkable consistency. Jakob Bjerknes, studying these boundary zones with particular intensity, realized they resembled battlefronts where opposing armies clashed along defined lines. He borrowed the military terminology, calling these atmospheric boundaries fronts. A cold front marked where advancing cold air pushed beneath warmer air, lifting it forcefully and creating lines of towering clouds and intense precipitation. A warm front showed where warm air climbed gradually over retreating cold air, producing broad shields of layered clouds and gentler, more extensive rainfall. This polar front theory, as it became known, provided meteorologists with a powerful conceptual framework for understanding mid-latitude weather systems. The Bergen models went further, describing the life cycle of what they termed cyclones, the large, rotating, low-pressure systems that dominated weather across temperate latitudes. These systems, they showed, were born along the polar front where cold polar air met warmer subtropical air. A small wave or perturbation along this boundary could grow, developing into a rotating vortex with cold fronts and warm fronts spiraling around a central low-pressure core. These cyclones would mature, intensify, and eventually dissipate in predictable ways, following patterns that could be recognized and anticipated. The elegance of the Bergen School's models lay in their ability to make sense of previously puzzling observations. Forecasters could now understand why certain cloud sequences appeared before storms, why winds shifted in characteristic patterns, why precipitation fell where it did. The three-dimensional structure of fronts and air masses explained phenomena that had seemed random or mysterious when viewed only from the surface. Tor Bergeron contributed crucial refinements to understanding precipitation formation within clouds, explaining how ice crystals and supercooled water droplets interacted in ways that determined whether clouds produced rain, snow, or nothing at all. These micro-physical processes, invisible to direct observation, could be inferred from careful analysis of cloud types and temperature profiles, adding another layer of physical understanding to weather analysis. Throughout the 1920s and 1930s, the Bergen School's methods spread across Europe and to North America. Meteorological services adopted the frontal analysis techniques, training forecasters to identify air masses and fronts on weather maps. The symbols they developed, the notation for cold fronts and warm fronts with their distinctive triangles and semicircles, became the universal language of weather analysis, still used on weather maps today. Yet even as these conceptual models improved understanding, the original vision of Wilhelm Bjerknes remained incompletely realized. The mathematical calculation of weather from physical equations, the true dynamic meteorology he had envisioned, still lay beyond practical reach. The equations were known, the physical principles understood, but solving them for the entire atmosphere required calculations so numerous and complex that no human forecaster could complete them quickly enough to be useful. One individual had already tried. Lewis Fry Richardson, an English mathematician and meteorologist, had spent years developing a scheme for numerical weather prediction, actually attempting to calculate a weather forecast by hand using the fundamental equations. His heroic effort, performed while serving as an ambulance driver during the First World War, consumed months of calculation, only to produce a forecast that was spectacularly wrong. The mathematical approach worked in principle, but the calculations were simply too vast for human computers to manage. The Bergen School's contribution was to bridge this gap, providing conceptual models that incorporated physical understanding, but remained practical for operational forecasting. Their methods allowed forecasters to think physically about the atmosphere without requiring impossible calculations. Air mass analysis, frontal identification, and cyclone life cycle models gave structure and predictive power to weather forecasting, while the technology caught up with Bjerknes's original mathematical vision. As the 1940s approached, meteorology had been transformed. The atmosphere was no longer an inscrutable mystery, but a physical system whose behavior followed comprehensible patterns. Weather maps had evolved from simple pressure readings to sophisticated analyses showing the three-dimensional structure of atmospheric systems. Forecasters understood not just what the weather was doing, but why, grounding their predictions in physical reasoning rather than purely empirical pattern matching. The mathematics of weather, as developed by Bjerknes and refined by the Bergen School, had prepared meteorology for its next great leap forward, though none could quite foresee what was coming. The tools to solve Bjerknes's original equations, to calculate weather from first principles, were beginning to emerge in laboratories far from Norway. Mechanical minds that would soon attempt what Richardson's human calculations could not accomplish. By the early 20th century, meteorologists had developed remarkable tools and theories for understanding the atmosphere. The Bergen School had given them conceptual frameworks. Weather stations dotted the landscape, and instruments probed the upper air. Yet despite all this progress, weather prediction remained frustratingly uncertain. Forecasts extended perhaps a day or two into the future, sometimes accurately, often not. The atmosphere kept its secret, dancing just beyond the reach of human comprehension. In England, a quiet mathematician named Lewis Fry Richardson dreamed of something revolutionary. Born in 1881 into a prosperous Quaker family in Newcastle, Richardson possessed a brilliant, unconventional mind that wandered across the boundaries of mathematics, physics, and meteorology. While others refined empirical methods and studied weather patterns, Richardson saw the atmosphere as something fundamentally mathematical, a fluid system governed by precise physical laws that could, in theory, be calculated. The equations existed already. The laws of motion, thermodynamics, and fluid dynamics had been written down decades earlier. These equations described how air moved, how temperature changed, how pressure systems evolved. In principle, if you knew the current state of the atmosphere everywhere, you could use these equations to calculate its future state. Weather prediction could become a mathematical certainty rather than an educated guess. But there was a problem, a magnificent, almost absurd problem. The equations were impossibly complex. Solving them for even a small region required thousands upon thousands of arithmetic calculations, each building upon the previous one. A single mistake would cascade through the entire forecast. The human mind, armed only with pencil and paper, could not possibly perform such calculations quickly enough to be useful. Richardson refused to accept this limitation. During the years leading up to the Great War, he developed a scheme for numerical weather prediction. He divided the atmosphere into a grid, creating boxes of air stacked upon one another. For each box, the equations would be solved, step by tiny step forward in time. Values would be passed between neighboring boxes, simulating how weather systems moved and evolved. He worked out every detail of this magnificent vision. In 1913, Richardson took a position at the Meteorological Office, where he could access real weather data. He needed actual atmospheric conditions to test his method: temperature, pressure, wind speed, humidity, all measured simultaneously across a wide area. Then came the war. Richardson, true to his Quaker pacifism, refused to fight, but volunteered with the Friends Ambulance Unit in France. Amidst the horror and chaos of the Western Front, this gentle mathematician carried with him a peculiar project. During lulls in the ambulance service, sometimes in cold dugouts while artillery rumbled in the distance, Richardson performed his calculations. Using weather observations from May 20th, 1910, he attempted to forecast the weather 6 hours ahead, after the fact, using historical data, but as a test of his method. For 6 weeks, he calculated, page after page filled with numbers, derivatives, approximations, corrections. The sheer volume of arithmetic was staggering. When he finally completed his forecast, reality delivered a harsh verdict. His predictions were wildly wrong. Where the actual pressure had changed by a small amount, his calculations showed enormous, physically impossible variations. The atmosphere he had simulated on paper bore little resemblance to the real sky of that May day in 1910. Richardson understood the problems. His grid was too coarse, his initial data imperfect, his methods crude. But the fundamental approach, he believed, was sound. In 1922, he published his work in a book titled Weather Prediction by Numerical Process. The volume was dense, mathematical, and visionary. In it, Richardson did something remarkable. He imagined a future solution to the computational problem. He described a fantastic forecast factory, a vast circular hall filled with thousands of human computers, each responsible for calculating conditions in one portion of the atmosphere. A conductor in the center, using colored lights, would coordinate their efforts, ensuring they all progressed through time at the same pace. Messengers would rush calculations between sections. The whole enormous apparatus might, Richardson estimated, just barely keep pace with the weather itself. It was a beautiful fantasy, but contemporaries found it impractical to the point of absurdity. Richardson's book was largely ignored. His failed forecast seemed to prove that numerical weather prediction was a dead end, too complex for practical application. Richardson himself moved on to other interests, studying the mathematics of conflict and human psychology. But the idea did not die. The equations remained valid. The mathematics sound. All that was needed was a different kind of computer, not thousands of people with pencils, but something faster, more tireless, more precise. That something emerged from the crucible of the Second World War. The conflict drove frantic innovation in calculation technology, initially for code breaking and ballistics tables. By war's end, the first electronic computers flickered to life, room-sized machines with vacuum tubes and primitive memories, but capable of performing arithmetic at speeds that would have seemed magical just years earlier. Meteorologists began to wonder, could these new machines tackle Richardson's dream? In 1946, at the Institute for Advanced Study in Princeton, mathematician John von Neumann became interested in weather prediction as a test case for computing. He assembled a team that included Jules Charny, a brilliant young meteorologist who understood both the atmospheric equations and their mathematical subtleties. Charny simplified the problem, focusing on the most important atmospheric processes and filtering out troublesome small-scale oscillations that had plagued Richardson's attempt. The team programmed their equations into ENIAC, one of the first electronic computers, a behemoth of 18,000 vacuum tubes consuming enormous amounts of electricity. In 1950, they succeeded. For the first time in history, a computer produced a weather forecast by solving the fundamental equations of atmospheric physics. The forecast was crude, covering only North America, predicting only the broad patterns of high and low pressure. But it worked. The machine had glimpsed the future sky. The transformation had begun. Through the 1950s and beyond, computers grew more powerful, meteorological models more sophisticated. What Richardson had attempted alone with pencil and paper, what he had imagined requiring thousands of human calculators, machines now accomplished in hours, then minutes. The forecast factory became real, shrunk down into cabinets of electronics, its conductor replaced by programmed instructions. Weather prediction had crossed a threshold, no longer merely an observational science, no longer dependent solely on pattern recognition and experience. Meteorology was becoming computational. The atmosphere's mathematical secrets, locked within differential equations too complex for human solution, were yielding at last to silicon and electricity. The dream of the quiet mathematician, scribbling calculations in a French dugout while war raged around him, was coming true. The computers had begun their work, churning through equations that described the atmosphere's behavior. But even as these electronic minds processed weather data with unprecedented speed, meteorologists understood that something fundamental was missing. The vast stretches of ocean, the remote polar regions, the deserts and mountains far from human habitation. these remained largely invisible to weather observers. Ships at sea reported conditions when they could. Weather stations dotted inhabited lands. But enormous gaps persisted in humanity's view of the global atmosphere. The weather moved through these blind spots, developing and evolving beyond human eyes, revealing itself only when it arrived at the next distant observation post. To truly understand weather, to see it as it actually was across the entire planet, meteorologists would need to rise above Earth itself. The dawn of the space age brought with it possibilities that seemed to belong more to imagination than reality. When the Soviet Union launched Sputnik in October 1957, that simple metal sphere orbiting overhead represented more than technological achievement. It demonstrated that humanity could place objects in space, that we could look down upon our world from above. The implications for meteorology were immediately apparent. If instruments could orbit Earth, they could observe weather continuously, watching storm systems develop over empty oceans, tracking clouds as they spiraled around centers of low pressure, witnessing the atmosphere's grand dance from a perspective never before possible. The dream took concrete form remarkably quickly. On April 1st, 1960, the United States launched TIROS-1, the television infrared observation satellite. The name itself spoke to its purpose. This was an eye in the sky, carrying television cameras that would photograph clouds from orbit. When TIROS-1 transmitted its first images back to Earth, meteorologists found themselves gazing at something that would have seemed like sorcery to weather observers just decades earlier. There, captured in grainy black and white photographs, were vast, sweeping patterns of clouds stretching across hundreds of miles. Weather systems that ground observers experienced as gradual changes in sky conditions appeared from space as coherent, organized structures with visible form and beauty. The satellite operated for only 78 days, but in that brief lifetime, it transmitted more than 22,000 images. Each photograph revealed new details about how weather appeared from above. Meteorologists could see the characteristic spiral structure of mid-latitude cyclones, the way clouds arranged themselves along frontal boundaries, the cellular patterns of convection over sun-warmed oceans. The images confirmed theories developed from ground observations and mathematical models, while simultaneously revealing unexpected details about atmospheric organization and structure. TIROS-1's success sparked rapid development. More TIROS satellites followed, each carrying improved cameras and instruments. The satellites captured images during both day and night, using infrared sensors to measure the temperature of clouds and Earth's surface, even in darkness. These temperature measurements provided information about cloud heights. Colder cloud tops indicated taller clouds that reached higher into the atmosphere, often associated with more vigorous storms. The true revolution came as satellites moved from experimental projects to operational tools. By the mid-1960s, weather satellites maintained continuous watch over Earth's atmosphere. Meteorologists could now track hurricanes from their birth as tropical disturbances off the African coast, watching them intensify as they moved westward across the Atlantic. The characteristic eye of a mature hurricane, that circular region of relative calm at the storm's center, appeared clearly in satellite imagery, surrounded by the towering eye-wall clouds where the most intense winds spiraled upward. This view from space transformed hurricane forecasting. Before satellites, Hurricanes over open ocean could surprise ships and coastal communities, their positions known only through occasional ship reports, or when reconnaissance aircraft flew into the storms. Now, meteorologists could see every tropical cyclone, monitor their development, and track their paths with unprecedented precision. The ability to watch hurricanes continuously from space saved countless lives, as more accurate warnings allowed communities time to prepare and evacuate when necessary. Satellites revealed weather patterns on truly global scales, the atmospheric circulation that scientists had theorized, the rising air near the equator, the descending air in subtropical regions, the meandering jet streams that guided weather systems across middle latitudes, all became visible from orbit. Images showed how vast rivers of moisture flowed through the atmosphere, how waves in the upper-level winds could trigger storm development, how weather in one part of the world connected to atmospheric patterns thousands of miles away. The technology continued advancing through the following decades. Geostationary satellites, positioned 22,000 miles above the equator, orbited at exactly the speed of Earth's rotation, allowing them to remain fixed above the same location. From this lofty perch, these satellites could watch entire hemispheres, photographing the same region every few minutes. Meteorologists could now create loops of images showing clouds evolving, storms developing, weather systems marching across continents in graceful time-lapse sequences that revealed the atmosphere's constant motion. Polar orbiting satellites complemented the geostationary platforms, circling Earth from pole to pole at much lower altitudes. As Earth rotated beneath them, these satellites viewed different parts of the planet on each orbit, providing detailed observations of high-latitude regions that geostationary satellites focused on equatorial regions could not see clearly. Between these two types of satellites, meteorologists achieved truly global coverage, no location on Earth beyond their view. The instruments aboard weather satellites grew increasingly sophisticated, beyond simple cameras and infrared sensors. Satellites carried microwave instruments that could peer through clouds to measure precipitation, detect winds over the ocean surface, and determine the vertical structure of atmospheric temperature and moisture. Lightning detectors counted electrical discharges from thunderstorms. Sensors measured energy reflected and emitted by Earth's surface and atmosphere across dozens of different wavelengths, each revealing different aspects of atmospheric conditions. This wealth of information flowed continuously from space to ground receiving stations, where it fed into weather forecast models and analysis systems. The computer models that had begun their work with sparse, unevenly distributed observations now received detailed information about atmospheric conditions across the entire globe. The improvement in forecasts was dramatic. Weather predictions extended further into the future with greater accuracy. Meteorologists could identify developing patterns days in advance, recognizing atmospheric configurations that historically preceded significant weather events. The satellite era also revealed Earth's atmosphere as a single interconnected system. Dust storms in the Sahara appeared as vast plumes of particles drifting westward across the Atlantic. Smoke from forest fires traced atmospheric wind patterns across continents. Volcanic eruptions injected material into the stratosphere, and satellites tracked its spread around the globe. The atmosphere's complexity and interconnectedness, long understood theoretically, became visually apparent in images from space. As meteorologists of the late 20th century gazed at satellite imagery that updated continuously. They possess capabilities that would have seemed miraculous to earlier weather observers. Yet the fundamental quest remained unchanged. Understanding the atmosphere's behavior, predicting its variations, keeping communities safe from severe weather. The tools had transformed beyond recognition, but the mission endured, now aided by these tireless sentinels orbiting high above, their electronic eyes forever watching the restless atmosphere below. As the space age ushered in an era of watching weather from above, meteorology was simultaneously transforming from within, powered by technologies that would have seemed like pure fantasy to the forecasters of earlier generations. The late 20th century brought tools that could peer inside storms, computers that could calculate atmospheric futures, and models of such sophistication that weather prediction became less about pattern recognition and more about understanding the fundamental physics of every cubic meter of air surrounding our planet. In the 1970s and 1980s, a new kind of radar began appearing across landscapes, distinctive domes housing rotating dishes that could do something previous weather radars could not. Doppler radar, named for the Austrian physicist Christian Doppler, who had described the frequency shift of waves from moving objects back in 1842, brought a revolutionary capability to weather observation. Traditional radar had shown where precipitation existed, painting regions of rain and snow as colored patches on a screen. But Doppler radar revealed motion itself, detecting whether raindrops were moving toward or away from the radar station by measuring the subtle frequency changes in the returning radio waves. This single innovation transformed severe weather warning. For the first time, meteorologists could see rotation inside thunderstorms, the telltale signature of tornado formation. They could measure wind speeds within hurricanes without sending aircraft into danger. They could watch the internal structure of storms as they evolved, seeing not just the result of atmospheric violence, but its very mechanism. The National Weather Service deployed a network of these radars across the United States, providing overlapping coverage that captured the atmosphere in motion across an entire continent. The warning times for tornadoes, once measured in mere minutes, began to extend. Communities received precious additional time to seek shelter, and the relationship between meteorologists and the public shifted. Weather forecasting became not just about tomorrow's conditions, but about imminent danger, communicated with increasing precision and confidence. Meanwhile, the computers that had struggled to complete a single forecast in Richardson's dream scenario were doubling in power with remarkable regularity. By the 1990s, supercomputers dedicated to weather prediction could perform trillions of calculations per second, dividing the atmosphere into ever finer grids of data points. The equations that Richardson had imagined requiring thousands of human calculators now ran through electronic circuits, solving the mathematical description of fluid motion, thermodynamics, and radiation transfer that governed every weather phenomenon. These computational advances enabled ensemble forecasting, a technique that acknowledged the fundamental uncertainty in atmospheric prediction. Rather than running a single forecast model, meteorologists began running dozens or even hundreds of slightly different versions, each starting with subtly different initial conditions or using slightly different mathematical approaches. The spread of these ensemble members revealed not just one possible future, but a range of outcomes, showing forecasters where predictions were confident and where they remained uncertain. A 5-day forecast in the year 2000 had become as accurate as a 2-day forecast had been in 1980. The steady march of improvement continued, driven by better observations, more powerful computers, and deeper understanding of atmospheric processes. Weather models began incorporating more of the Earth system, recognizing that the atmosphere did not exist in isolation, but interacted constantly with oceans, ice, land surfaces, and vegetation. Ocean temperatures influenced hurricane development. Soil moisture affected rainfall patterns. Snow cover altered regional temperatures. The models grew more comprehensive, attempting to simulate not just the air but the entire coupled system of Earth's climate. This convergence brought meteorology and climate science into closer relationship, as the same fundamental physics governed both tomorrow's thunderstorm and the long-term evolution of global temperature patterns. The Internet revolution of the 1990s democratized weather information in ways previous generations could hardly imagine. Data that once flowed only to government agencies and universities became available to anyone with a connection. Satellite images updated continuously. Radar loops played in real time. Forecast models that once required security clearances to access appeared on public websites. Weather enthusiasts around the world could examine the same sophisticated tools professional meteorologists used, participating in observation and discussion of atmospheric phenomena. Automatic weather stations proliferated, scattered across landscapes and even mounted on personal homes, reporting temperature, pressure, humidity, and wind to central databases every few minutes. This crowdsourced meteorology filled gaps in official networks, providing hyper-local observations that captured the fine details of weather patterns. Storm chasers equipped with mobile technology sent reports from the field, adding human context to the mechanical observations of instruments. By the early 21st century, weather forecasting had evolved into a system of systems, a global enterprise involving satellites in orbit, radar networks on land, ocean buoys reporting from remote seas, weather balloons ascending twice daily from hundreds of stations, aircraft measurements from commercial flights, and ground stations beyond counting. All this data flowed into computational centers where models ran continuously, updated hourly, producing forecasts that extended weeks into the future. Yet for all this technological magnificence, meteorology retained its essential humanity. The forecaster remained crucial, interpreting model outputs, recognizing patterns, understanding local effects that models might miss, and communicating forecasts in language that served human needs. A percentage chance of rain meant something different to a farmer planning harvest than to a wedding planner or a highway department preparing for winter storms. The science continued evolving. Research into chaos theory revealed fundamental limits to weather predictability, suggesting that perfect forecasts beyond about 2 weeks might remain forever out of reach due to the atmosphere's inherent sensitivity to tiny perturbations. Yet within those limits, steady progress continued. Understanding of climate patterns like El Niño and La Niña improved, allowing seasonal forecasts that helped agriculture, water management, and disaster preparation. As meteorology moved through the 21st century, new questions emerged. How would weather patterns shift as the climate changed? Could forecasts help societies adapt to new atmospheric behaviors? The same tools that predicted tomorrow's weather began examining possible futures decades away, exploring how the atmosphere might respond to different human choices. Through all this change, the fundamental wonder remained. Each sunset painted clouds in colors no artist could fully capture. Each thunderstorm demonstrated power beyond human scale. Each snowflake carried intricate geometry. The atmosphere, that thin envelope of air between Earth and space, continued its eternal dance of heating and cooling, rising and sinking, swirling and flowing, creating the weather that shaped every human experience. From ancient eyes watching clouds to satellites observing from space, from Aristotle's philosophical speculations to supercomputers solving physics equations, humanity's journey to understand weather had been long and remarkable. And still, the atmosphere held mysteries, still offered surprises, still reminded us that for all our knowledge and technology, we remained participants in natural systems far greater than ourselves, dwelling beneath an ever-changing sky that would continue its magnificent performance long after we were gone. As we bring to a close our journey through the story of meteorology, from those first curious glances at the sky to the birth of atmospheric science, we hope these tales of clouds, winds, and wonder have gently carried you through the evening. Thank you for joining us on this peaceful exploration of how humanity learned to read the language of the heavens. If these calm adventures have brought you comfort, we'd love to have you with us again. Like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way here. And now, as the night deepens and your mind settles like a gentle fog, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.